Last day of SPLASH'23. So this session is about cost precision trade-offs and acceleration. And we are going to start with a talk on ADCL, acceleration-driven closed learning for constrained horn clauses. So this is work by Florian Frohn and Jürgen Giesel from Aachen University. And Florian is going to give the talk. So Florian, the floor is yours.
So thank you for the introduction. So ADCL is a new calculus to analyze the satisfiability of constrained horn clauses, or CHCs for short. More precisely, we're looking at linear CHCs. We'll explain what that means in a minute. If you're not familiar with CHCs, then for the sake of this talk, you can simply think of them as transition systems, and I will comment on that throughout the talk from time to time. And as you all can already see from the name of the calculus, acceleration is the core ingredient here, so I will explain what that means in a minute. But before that, let us have a look at one of those CHCs to see what they look like. So essentially, this is just first-order logic, where we are looking at restricted forms of formulas. So all these formulas are implications. We always have at most one uninterpreted predicate symbol on the left-hand side, one uninterpreted predicate symbol on the right-hand side. And in addition, we have some constraint with respect to some background theory. So in this case, that would be integer arithmetic. So in a nutshell, this formula tells you if f of xy holds and x is bounded by 5,000, then f of x plus 1 y holds as well. And if you prefer to think of that as a transition system, then, well, f is basically your location in your control flow graph, and then this transition here tells you if f is reachable with the valuation xy and x is bounded by 5,000, then f is also reachable with the valuation x plus 1 y. And if you go from CHCs to transition systems, then unsatisfiability becomes unsafety and satisfiability becomes safety. Okay, now the goal of acceleration techniques is to take a clause like this one here, which is conjunctive because we do not have disjunctions in this constraint here. So in general, the theory part here may also contain disjunctions. And it's recursive because we have the same predicate symbol on the left-hand side and the right-hand side. Of course, in general, that does not have to be the case. So we start with such a clause, and then our goal is to compute a new clause, which I called phi plus here. And essentially, the idea is that everything that can be derived from your original clause via resolution in arbitrarily many steps can be derived from your new clause in just a single step. Or in the setting of transition systems, everything that is reachable with your original transition in arbitrarily many steps is now reachable with your new learned transition in just a single step. So more formally, the ground instances of your CHC, which result from instantiating the variables with some substitution that satisfies our constraint. So the ground instances of the new clause are the union over everything that you can get from your original clause via resolution. So this notation here simply means that we resolve phi with itself n times. Okay, so that's the basic idea. What does that mean for our example? Well, we introduce a new variable, which is called n here. It needs to be positive. And now this new clause should simulate n steps with our original clause in just a single step. So instead of incrementing x by 1, we increment it by n. And then we need this additional condition here, which guarantees that the condition of our original clause is indeed satisfied throughout n steps of resolution. So that's how it works. And just to convince you that this is not something that I made up, there are quite a few approaches in the literature that present techniques how to compute such accelerated transitions or accelerated clauses. Okay, now why is it a good idea to use these acceleration techniques for satisfiability of constrained horn clauses? To illustrate that, I would like to introduce my leading example, which consists of these three clauses. The first one is what we call a fact. It does not have an uninterpreted predicate symbol on the left-hand side, but just a constraint. So in the setting of transition systems, that would basically correspond to your initial states. So you start with something, so you start at location F, and X is bounded by 0 and Y is bounded by 5,000. Then our second clause is a recursive rule, which now has a disjunctive condition. So here you can see the disjunction here, and the clause that we've seen at the previous slide basically corresponds to this first case here, okay? And then the last clause is what we call a query. So the right-hand side does not contain any uninterpreted symbols, but it's simply bottom. And that corresponds to your error states in the setting of transition systems. So once you've derived f of 10,000, 10,000, you immediately get a contradiction, which means unsatisfiability, and in the context of transition systems, that would be unsafety. Okay, so how can we prove unsatisfiability of such a set of CHCs in a kind of traditional way? Well, we could do it like that. We start with our fact, where we instantiate the variables by suitable values, like x with 0 and y with 5,000. Then we obtain this state here. Now we can apply our second clause 5,000 times. More specifically, the first case or the first implicant of our clause. So an implicant is just a conjunctive variant of our potentially disjunctive clauses. Now this first implicant applies 5,000 times because it applies whenever x is bounded by 5,000. So if we start with 0 and increment it 5,000 times, then we end up in this state here. Then the second implicant of our clause applies 5,000 times, which increments x and y simultaneously, because y is now set to y prime, which is equal to y plus 1. So after 5,000 steps, we end up in this state, and then we can apply our last clause and get a contradiction. So what's wrong with this reasoning? Basically nothing, but it takes more than 10,000 steps. So if you use a technique that relies on some kind of iterative deepening, like bounded model checking, for example, it's going to work eventually, but it's going to take some time to unfold the relation like 10,000 times. So we propose a different kind of reasoning, where we first have a close look at implicant 2a, and I already mentioned that this is the same clause that we've seen on the previous condition, so we already know what happens when we accelerate it. We get this new clause here. Then we can have a close look at implicant 2b accelerated as well, and in this way we obtain clause number 5, where now x and y are incremented by n instead of just by 1. And then we get a much shorter proof, which looks like that. So again, we start with our fact and get f of 0, 5,000. Now we can simulate 5,000 steps with clause 2a in a single step and jump straight to f of 5,000, 5,000. Then we can use our second learned clause to simulate 5,000 steps with clause 2b and jump straight to f of 10,000, 10,000. And then we can apply our query after just 3 resolution steps, and we get a much shorter proof. Okay, so this reasoning was kind of ad hoc. Now we wanted to formalize that in a way that we can automate. And to this way, we came up with our calculus ADCL, which essentially consists of these 4 rules here, which may look a little bit shocking, but that's essentially the formalization of our whole technique. So if you see it from that angle, it's not that shocking anymore. So I'm going to give you the high-level intuition of those 4 rules first, and then we are going to see how they operate on our example, okay? So the states of our calculus are those pairs here, where the first component is what we call a trace. And a trace is simply a sequence of CHCs, which always starts with a fact, so an initial state, if you want to see it like that. And as an invariant of our calculus, the resolvent of our trace, so if you just resolve those clauses from left to right, always has a satisfiable condition. So in the setting of transition systems, this sequence corresponds to an actual program run, okay? So our goal is to find such a trace that ends with a query, because it always starts with a fact. So if it ends with a query, then we have derived the contradiction, so we've proven unsatisfiability. The second component of our states is a vector of sets of blocking clauses. And here the idea is that the elements of the last set of this vector may not be used for the next resolution step. So in this way, we can block certain parts of the search space such that we do not visit them again. Okay, the CHCs that we are analyzing are in this set capital pi here, And this abbreviation here means syntactic implicant projection, which is a bit technical. I'm not going to go into the details here, but essentially that tells us that we do not use the clauses as they are, but we use those implicants, those conjunctive variants of our clauses for resolution. And that's important because in this way we make sure that only conjunctive clauses end up on our trace, and in this way we can use our acceleration techniques, which only work for conjunctive clauses. Okay? So what this first rule does is it simply picks one of our conjunctive variants of our clauses, it appends it to our trace, and it appends an empty set of blocking clauses here. So it just makes one step with a CHC. Okay, the second rule is for acceleration. So if our trace has a suffix which is recursive, then we plug this suffix into an acceleration technique. In this way, we derive a new clause. We replace our recursive suffix with our new learned clause, and we block this learned clause for the next step. So why do we block it? Because these learned clauses, these accelerated clauses, basically correspond to transitive closures. So using them twice in a row is kind of pointless. Everything that can be done with 2 occurrences of such a clause can also be done with just a single occurrence of them. And for that reason, we don't have to consider traces where the same accelerated clause occurs twice subsequently. Okay, our third rule is for the case that our trace has a suffix which is redundant for a certain notion of redundancy. I will explain a little bit more about that later on. And in this case, we can backtrack. And backtracking simply means that we drop the last element of our trace and block it. And there's a second case where we can backtrack, which is, well, when we are stuck, when all clauses are either blocked or appending them to our trace would result in a trace whose resolvent has an unsatisfiable condition. In this case, we can backtrack as well, because there's no way to make progress from such a state. Okay, so how does that work on our example? Here are our 3 clauses again, and the learned clauses are grayed out because we haven't learned them so far, right? And then we can start to construct our proof. And the initial proof state always looks like that. So the trace is empty, and we have an empty set of blocking clauses here, so nothing is blocked for the first step. Then we start with a fact, because as I mentioned, the first element of the trace always has to be a fact, with our rule step, and we append another empty set to our blocking clauses here. And on the right, I show you one possible model for the resolvent of our trace, just to give you some idea where we are in the state space. So there are many other models here. Those are not unique. They are just to give you some idea where we are. Okay, now we can apply our second CHC, but as I mentioned, we do not apply it as it is, but we use one of those conjunctive variants, in this case, implicant 2a. And what's important is that we compute these implicants lazily. So I just highlighted implicant 2a here because our implementation wouldn't care about implicant 2b at this point. And that's important because there can be exponentially many of these implicants in practice. Okay, now I'm going to do something stupid, which wouldn't be done by our implementation, but I want to illustrate something by doing that. So let's make another step with our clause 2a. Then we end up in a state like this here, where x is, for example, 2. Okay, but at that point, we should really apply our acceleration technique because our trace has a recursive suffix, namely clause 2a. And we've already seen what happens when we accelerate it. We obtain clause number 4 here, which increments x by n and can simulate arbitrarily many steps with clause 2a. So we replace the last element of our trace with our learned clause, and we block this learned clause for the next step. Okay, at this point, our trace has a suffix which is redundant. Why is that? Well, these clauses here together, 2a and 4, they simulate effectively at least 2 and possibly more steps with our clause 2a, right? Because 4, remember, corresponds to the transitive closure of 2a. So it can simulate 1 or more steps with clause 2a. So if you take these 2 clauses together, they can simulate 2 or more steps with clause 2a. That's strictly less general than just clause 4, which can simulate 1 or more steps with clause 2a. Hence, these two clauses together are redundant, because everything that can be done with them can also be done with clause number 4. Hence, we can now backtrack and block clause number 4 for the next step. Now we are again in a state where our trace has a redundant suffix, because 2a is strictly less general than clause 4. So we can backtrack once more and block clause 2a. And now we can do another step with our accelerated clause number 4 and end up in this state. So that's basically the reason why I did this somewhat stupid step here, where I should have used where I should have used acceleration straight away, and instead I used clause number 2a a second time. And this way we ended up in a state where we have a redundant suffix, so that I could illustrate how to use the rule covered. Okay, so at this point we are in a state like x 5,000 and y is 5,000, so we can use the second implicant of our clause number 2, which is implicant 2b, and it increments x and y by 1. And now we can use acceleration again, because clause 2b is recursive, and learn our second accelerated clause, clause number 5, which we've seen before as well. In this way, we can simulate arbitrarily many steps with clause 2b at once, and finally apply our query, clause number 3, to derive a contradiction. And now we've successfully proven unsatisfiability of our CHCs. Okay, now we haven't seen how to use the last rule of the calculus. So just to illustrate that, let's forget about clause 3. Let's pretend that it doesn't exist. Then the last step doesn't work anymore. And now we are in a situation where we are stuck, because clause number 5 is blocked explicitly, and clause number 2b is blocked implicitly here, because clause number 2b is redundant with respect to clause number 5. It's strictly less general. So if we block a clause with these blocking clauses, we implicitly also block everything that is redundant with respect to them. Okay? So we cannot use clause number 2b, and we can also not use 2a or 4, because they require that x is bounded by 5,000, but the last element of our trace is clause number 5, which requires that x is greater or equal than 5,000. So we cannot apply them either, hence we are stuck, and in this case we can backtrack using our last rule. So we drop clause number 5 and block it. Now we could continue with this example by doing more steps and backtracking and so on. Then eventually we would reach a state like that, where the trace is empty and our only fact, clause number 1, is blocked. And whenever we reach a state like that, where the trace is empty and all facts are blocked, then we have proven satisfiability. So then we have shown that our set of clauses is satisfiable. Okay, so that's how our calculus works. Let's look at some numbers, because we've implemented all of that in our tool LOAD, the loop acceleration tool, and compared it to a few other tools. So the implementation of bounded model checking in Z3, the implementation of the spacer algorithm, which is kind of the state-of-the-art algorithm for satisfiability of CHCs, and it's also implemented in Z3, and transition power abstraction, which is implemented in Golem, and Seeger loop, which is implemented in Eldarica. And as you can see, our implementation cannot prove satisfiability at the moment, because we use certain approximations that are unsound for satisfiability. So far we have focused on unsatisfiability. We'll talk a little bit more about that later on. But you can see that for unsatisfiability, we are quite competitive. So bounded model checking is a bit more powerful. Spacer and LOAD are almost equally powerful. And you can see that we can solve quite a few instances that cannot be solved by any other tools. And if we look at these instances a bit more closely, then you can see something quite interesting. So the counterexamples, the refutations that LOAD finds, are pretty short, so 15 steps at most. Now, of course, these refutations use our learned accelerated transitions that can simulate many, many steps at once. So you can map these resolution proofs back to proofs that only use original clauses that were already part of the input. And if you do that, then you get proofs of this length here on the right-hand side. So something like, I think, 684 million steps. Well, good luck with finding something like that with bounded model checking. So for these problems, you really need techniques like acceleration. And if we look at the runtime, well, you can see that bounded model checking, spacer, and our implementation, so ours is the black line, the yellow one is bounded model checking, and the blue one is spacer, are all essentially equally fast in practice. Okay, so to conclude, we've introduced a new calculus that can prove satisfiability and unsatisfiability of constrained Horn clauses, even though our implementation is currently restricted to unsatisfiability. It's refutationally complete, so if your set of CHCs is unsatisfiable, then you can prove it with this calculus. Unfortunately, it does not terminate in general, so even if you impose some reasonable restrictions on the strategy, how to use the rules of our calculus, you still cannot guarantee termination of the calculus, unfortunately. I've talked about this notion of redundancy quite a bit in this talk. Unfortunately, automating that is quite challenging, so that's one of the points where we have to use approximations. So we use a sufficient criterion for redundancy in our implementation, which is one of the reasons why we cannot prove set. And our acceleration techniques are, of course, incomplete. I mean, you cannot always compute these transitive closures precisely. So here we sometimes have to resort to approximations, and those approximations are also just sound for unsatisfiability. But on the bright side, it's orthogonal to the state of the art, so we can prove quite a few things that other tools cannot prove, and it finds significantly shorter refutations than other tools due to its use of acceleration techniques. So thank you very much for your attention.
Okay, thank you very much, Florian, for the talk. So are there any questions in the room or online? So please. Yeah. Mine. Take the broken one.
Okay, thanks again for the comprehensible talk. I mean, for humans, it's quite clear that we want to instantiate n to 5,000 in your example, but how does your tool instantiate those variables?
So let's go back to this example. So in this example, I showed you these models on the right-hand side, right? The point is that in practice, these models are not part of your state. So the SMT solver that's running in the background just chooses any model, but it can change to a different model at any point. So let's consider this state here, where the last clause is clause number 4. You're perfectly right. Now the SMT solver might say, okay, let's set n to 1. That's perfectly okay. In the next step, well, we cannot use clause number 4 again because it's blocked. We cannot use clause number 2a again because it's blocked. So all we can do is we use clause 2b, and clause 2b requires that x is at least 5,000. So at this point, when we add the constraint of clause 2b to the SMT problem, the SMT solver has to switch to a different model where n is instantiated with 5,000. So essentially, the important bit here is that the model is not part of the state, so it can change at any point. And hence, if we make a bad decision with respect to this new variable n, it's not such a big deal.
And then it jumps back and forth and finds the n equals 5,000 the next time.
Yes, I mean, when you say it jumps back and forth, the SMT solver jumps between different models. That's correct. But our calculus is not affected by that because the model that the SMT solver finds for the resolvent is not part of the state. So in this step here, from this state to that state, the SMT solver can simply switch to a different model, but that doesn't affect our calculus at all. So we do not have to do additional steps with our calculus due to that.
Okay, thank you. And any other question, Andy?
Okay, so this acceleration technique seems to rely on the fact that instead of doing a single step, you can do like a symbolic number of steps. So you can introduce the n, which gives you the clause 4, and that's the thing which allows you to do these sort of quantum leaps. Okay, so you can sort of do that when your constraint system here is a system of inequalities, because you can introduce a fresh variable there. Okay, so that sort of begs the question of, if you're working over different constraint systems, how can you then symbolically capture the fact that you're doing lots of compositions of the constraints and represent the number of compositions symbolically with a number? Have you got any answers to that? I don't know if that's a silly question. I've got no idea.
So if I understand your question correctly, you're wondering what happens if so here we have equalities essentially, right? The new value of x is the old value of x plus 1. That's an inequality. So you are wondering what happens if this is an inequality and x gets just set to a larger value, but we don't know how much it is increased specifically, right?
Oh, yeah, that's true. No, I wasn't even wondering that. I was wondering about what happens if you operate over a different constraint system. When you're outside the world of equalities and inequalities, because the systems, there are lots of different constraint systems which are interesting in sort of program analysis.
So you mean like different theories?
Yeah, like different theories.
Okay. So different theories are very interesting.
Okay.
So I think if we go to reals or rationals, that's going to work basically in the same way. We have some ideas for arrays. That's basically work in progress. I hope that we have something for that in the next year. Bitword vectors should work without too much hassle. Floats are going to be a nightmare. So it really depends on your theory. So you can integrate any theory into this calculus where you have these acceleration techniques, but for every theory you have to develop these acceleration techniques from scratch, essentially.
Okay. That makes sense. Thank you.
Yeah, thank you very much. So I also have one question that is maybe slightly connected on this question. When I look at the examples that you have shown, it kind of reminds me of what we would see if we analyze a program and try to have a relation between precondition and postcondition. So it's a kind of relational analysis. And of course, if we do it with some abstract domain, abstract interpretation technique, and say we use polyhedra or different abstraction, the path from the problem to the solution would be slightly different. We would use widening, we would use abstract postcondition. So my question is, did you try to look at a correspondence between the resolution steps that you would do and the analysis steps that we would observe in such cases?
Not really. So the thing is that we were mainly interested in proving unsatisfiability, and most of the existing techniques, in particular abstract interpretation-based techniques, use over-approximation. So if you get to an error state, you still have to do some kind of post-verification that you actually have a real path to the error. And we wanted to avoid that, so we used these acceleration techniques, which are precise if they apply, so that we do not have to do this post-verification step. So that's, I think, a crucial difference between this approach and many others.
Fair enough. Any more questions? I see no online questions, so I think we are going to thank Florian again for the nice talk and the discussion. Okay, cool. Okay, so now we are going to move to the second talk, which is about unconstrained variable oracles for faster static analysis by Vincenzo Arceri, Greta Dolcetti, and Enea Zaffanella. So, and Greta is going to give the talk.
Okay. Good morning, everyone. I'm Greta Dolcetti from Ca' Foscari University of Venice, and today I'm going to present to you unconstrained variable oracles for faster numeric static analysis, which is a joint work with Vincenzo Arcieri and Enea Zaffanella, both from University of Parma. So we are in the context of static analysis by abstract interpretation. And as we know, the abstract interpretation process may suffer some inefficiencies. There are many ways to tackle these inefficiencies. Some canonical solutions, for example, are choosing a different abstract domain. So we can go, for example, from polyhedra to the octagon domain, being more faster, but losing some precision. Or we can choose different implementation of abstract operators inside our domain of choice to be more efficient. Another technique is abstract compilation, whereas for abstract compilation, we intend a set of techniques that consist of the rewriting the intermediate program representation adopted the analyzer. In this case, the goal is to optimize the abstract execution, and we are in a context where there's a trade-off between accuracy and efficiency. So we are targeting efficiency, and we are okay with losing some accuracy wherever it happens. We know that traditionally, efficiency of the evaluation process may be improved by propagating known information. Our goal here in this work is to show that these improvements may also be achieved by propagating unknown information. To explain that, I have to introduce the concept of likely unconstrained variables, and I want to do that with a simple example. So let's suppose we are doing a sort of analysis with intervals, and after some analysis steps, we have information about these two variables, expression, which is bounded by 1 and 12, and y, which is unbounded. We know nothing about y. Then let's suppose that we want to analyze this assignment, which is x is equal to y plus expression. And the end, after the analysis of this assignment, what we have is that we have the same information about expression and y. And for x, we do not have any information. In this context, y is likely unconstrained. Therefore, x is likely unconstrained too. So if no information is known about y, then it's likely that little to no information will be known about the whole expression that contains y. So there is little to no incentive in providing an accurate and maybe expensive evaluation of the whole expression that contains a variable which is likely unconstrained. The idea here is to identify the variables that we will call likely unconstrained variables for which no information will likely be available at a given program point. And once we identify them, what we want to do is to propagate this lack of information throughout the whole program. The goal, as I said, is to simplify the analysis and improving efficiency. In our work, we have 3 major steps. The first one is a data flow analysis, for which we have 2 variants. The first one is a relational variant for to be used with relational domains such as polyhedra. The second one is a no-relational variant for to be used with no-relational domains such as intervals. What they do is that basically they analyze a statement at the time, and after the analysis of that statement, they update the set of variables that are likely unconstrained after the execution of that statement. Then we have 2 kinds of propagation to propagate the unknown information, and they are the existential propagation and the universal propagation. After that, once we have computed the information about the likely unconstrained variables, you have to apply the program transformation step to create the simplified version of the program, of the intermediate representation of the program that we are going to analyze. Here, as I said, we have 4 different variants, which are given by the combination of the 2 different oracles, relational and no-relational, and the 2 different kinds of propagation, existential and universal. These are heuristic solutions, so they are subject to both false positives and negatives. But the final analysis is always sound. I want to mention that we have 4 different variants because we are looking for an aggressive variant in order to tackle major efficiency improvement. Now, let's look at the no-relational oracle and the formalization for the data flow analysis. So here, we're analyzing, in the first example, the non-deterministical assignment. And what we do here, it's basically we add the variable on the left-hand side of the non-deterministical assignment into the likely unconstrained set. For other assignment with 2 variables, or 1 variable and 1 constant, what we do is that we remove the variable from the like-and constraint set if we are able to say something about the right-hand side of the assignment. So if both variables are not like-and constraint, or if we are doing some operation such as the subtraction from a variable by itself or multiplication by 0, so that we can say something about the right-hand side. In the same way, when we are analyzing Boolean guards, we remove one variable from the like-and constraint set if the other one is not like-and constraint. The relational oracles has a similar implementation, but as I said, it's thought to be used with relational domains, such polyhedra, so we're aiming to be more conservative. For the non-deterministic assignment, we have the same application, so we simply add the like-and constraint variable to the like-and constraint set. And for the assignment, what we do is that we remove all the variables if you're using some specific operation, such as plus or minus. Otherwise, we adopt the non-relational variant. And for the Boolean guards, we simply remove all the variables from the like-and constraint set. So, as I said, these oracles are heuristics, so they are subject to false positives and negatives. Here, there's an example of false positives. So let's suppose that this is the whole program that we are analyzing. The first statement is an assignment. Y is assigned to 0, so it's not like a constraint since 0 is a constant. Then x is equal to y times z. But since z is likely unconstrained, then x is likely unconstrained too, even though the interval analysis would compute x as 0, because that's a multiplication by 0. Whereas for the false negatives, let's suppose that, as I said, this is the whole program that we are analyzing, and let's suppose that we have two Boolean guards. Y is greater or equal than 0, and z is less or equal than 0. Then we remove y and z from the like-and constraint set when we are evaluating these Boolean guards. Then we have an assignment, x is equal to y plus z. X is considered constraint here, even though the interval analysis would compute minus infinite plus infinite. Looking at the propagation, as I said, we have two variants, two different propagation. We have the existential value propagation, for which a variable is part of the like-and constraint set at the beginning of a basic block if there's at least one incoming edge along which that variable is like-and constraint. Dually, the universal propagation, a variable is part of the like-and constraint set at the beginning of a basic block if that variable is like-and constraint along all incoming edges on that basic block. Whereas for the program transformation step, as I said, this is the algorithm that rewrites our initial intermediate representation of a program into a new intermediate representation, which we are later going to analyze. Here, we are working on the input CFG in the intermediate representation, and since this is executed after the data flow analysis, what we have is that we have the information about the variables in the CFG. So they are already mapped, and we know what variables are likely to be unconstrained. What we do here is that for each basic block, we compute and we retrieve the information about the variables that are likely to be unconstrained after the execution of that basic block. Then, for each statement, which is an assignment, we check if the left-hand side of the assignment is likely to be unconstrained after the execution of that basic block. If that's the case, we simply replace the left-hand side of the assignment with the non-deterministic assignment. So we basically simplify that assignment. But let's see that in work with an example. Let's suppose that we are analyzing this simple CFG with 4 basic blocks, B0, B1, B2, and B3. In this case, we are using a non-relational oracle with existential propagation. So at the beginning of the analysis, what we have is that all the variables are likely unconstrained. So x, y, and z are all likely unconstrained variables. Then we start with analyzing B0. We have an assignment, 0 is equal to, x is equal to 0. 0 is a constant, therefore x is removed from the likely unconstrained set. So after the analysis of B0, the likely unconstrained set is made by y and z. Then we proceed with analyzing B1. So we have a Boolean guard, y is less than 0, 0 is a constant, y is removed from the likely unconstrained set. Then we have two assignments, x is equal to x plus 1. Since x is likely unconstrained and 1 is a constant, we do not have to update the likely unconstrained set. y is therefore assigned to y plus 1, and for the same reason, y it's not likely unconstrained, and 1 is a constant. So at the end of execution of B1, we have that the likely unconstrained set is composed just by the variable z. Then we analyzed the basic block B2. For the same reason, we have a Boolean guard, y is greater or equal than 0, and since 0 is a constant, y is removed from the likely unconstrained set. Then we have the same assignment, x is equal to x minus 1, and therefore x is not, this assignment is not modified in the likely unconstrained set. But then here we have y is equal to z times 2. Since z is likely unconstrained, then y is added back to the likely unconstrained set. So the resulting likely unconstrained set after the execution of B2 is made by y and z. To compute the likely unconstrained set that holds before the analysis of B3, we have to reason about which kind of propagation we are using. In this case, we are using the existential propagation. Therefore, the likely unconstrained set before the execution of B3 is made by the union of the likely unconstrained set computed in the two previous basic blocks. So it's composed by y and z. Then we are going to analyze the statement, the assignment inside B3. This is x is equal to x plus y. But since y is in the likely unconstrained set, then x is added back to the likely unconstrained set. So therefore, after the execution of B3, we have that all variables are likely to be unconstrained. After we executed this data flow analysis, we had to apply, as I said, the program transformation step. So here, we have rewritten this CFG into a simplified one. And as we can see, we are rewriting two statements into non-deterministical assignment. The reason for that is that, as I said, here, y in the basic block B2, it's likely to be unconstrained after the execution of B2. So the assignment y is z times 2 is rewritten into the non-deterministical assignment. And for the same reason, x is equal to x plus y, since x is likely to be unconstrained after the execution of B3, is rewritten as the non-deterministical assignment. Here, we are analyzing the same CFG with the same non-relational oracle, but a different kind of universal propagation to highlight the differences. So what we have is that, of course, all the variables are likely to be unconstrained at the beginning of the analysis, and therefore then we have the same result, the same like unconstrained for basic block B0, so it's made just by y and z, B1, just z, and B2, y and z, because the analysis proceeds as before. But here, for basic block B3, once again, we have to reason about which kind of propagation we are using. In this case, the universal propagation. So here, the likely unconstrained set that holds before the execution of B3, it's composed by the intersection of the two previously computed likely unconstrained set. So in this case, it's the intersection between z and y and z, so it's composed just by z. So here we proceed with the analysis of the basic block B3 with the assignment x is equal to x plus y. Since now neither of that variable is likely to be unconstrained, we do not need to update the likely unconstrained set, so that at the end, after the execution of B3, just the variable z is likely to be unconstrained. Then we proceed with the program transformation step. And here we can see that this time we are simplifying just one statement, just the statement in B2. The reason for that is, as before, this left-hand side of this assignment, after the execution of B2, it's likely to be unconstrained. So we simplified it. But this time, if we are looking at B3, we were previously simplifying. This time, x is not likely to be unconstrained after the execution of B3. So we are not simplifying that, resulting in a less aggressive simplification. For the experimental evaluation of this work, we adopted two benchmark suits. The first one is composed of 34 files distributed with an analyzer PAGAI and used for the worst-case execution time analysis. Since these files are very synthetic, we are not focusing on them now, and you can find the details on the paper. Here, we are focusing on 10 files distributed with SVCon without the implementation on 10 Linux drivers. And for our analysis, we adopted two domains. the interval domains, and the factor polyhedra implemented in the pp-lite library. We implemented our analysis in two modules, CLAM and CRAB, which are modules of the C-ORN verification framework. CRAB is the C++ library for static analysis, which offers the implementation for many abstract domains and fixed-point engine. It relies on its own intermediate representation, which is called CRAB-IR, from which here you can see an example. This is an important example because this is exactly what we are working on. This is the CFG that we are going to rewrite. Also highlighted here, you can see havoc, which is the statement inside the CRAB intermediate representation for the non-deterministic assignment. So this is what gives the name in the next step to our analysis. CLAM, instead, it's the front end for CRAB, and it basically takes in input the C source code, it transforms it LLVM bit code, and then it creates the CRAB intermediate representation. So it's creating the CFG for which we are working on in the next step. Another useful tool present in this framework is CLAMDiff. So CLAMDiff, it allows us to compare the invariants computed by two different analyses in a semantic way so that we can say which one is more precise. Basically here, what we have is that we have implemented two pipelines. The first one is the classical pipeline. So we start from the C source code that we are analyzing, then our actor clang and clam preprocessing step transform that into LLVM bits code so that then clam creates the original CRAB CFG, the original CRAB in CRAB intermediate representation. Then we are doing the target analysis, and what we obtain are the original target analysis invariant. On the other end, where we are applying our implementation, what we add is that we start with the C source code as well. We apply clang, and clam preprocessing creates the LLVM bit code. Then clam creates the original CRAB intermediate representation. Then we apply our data flow analysis, which is called AVOC analysis, from which we obtain the information about the unknown variables inside our CFG. After that, we apply the program transformation step, which is called AVOC propagation, from which we obtain the AVOC CRAB IR, so the simplified version of our intermediate representation. Then we apply the same default target analysis on that simplified CRAB intermediate representation, from which we obtain the AVOC target analysis invariant. Once we have computed the two invariants from the classical analysis and from the simplified analysis, we compare that with CLAMDiff in order to see whereas there are any precision losses. The first thing that we did was to evaluate the statement in our benchmark. Here we're seeing the 10 Linux driver, and for each of them, you can see in the first column the name, then the number of statement, and then the 4 variants. And for each variant, they are reported how many statements of the original statement are simplifying, and the time expressed in milliseconds, from which it is taken for the data flow analysis and the program transformation step. What we can see here is that we have 4 different approaches. And for the most aggressive one, so the no-relational oracle with existential propagation, we are simplifying between 4.5% of the original statement and up to 82.1% of the original statement. Whereas in average, we are simplifying 33% of the original statement, so a lot. And for the most conservative oracles, which is the relational oracle with the universal propagation, we are simplifying between 0.2% of the original statement and 10.9% of the original statement, with an average of 4.1%, so much lower. So here we see that relational oracles are too conservative to luckily bring any efficiency improvement, whereas no-relational oracles are rather aggressive, so they may trigger significant efficiency improvement. So for the evaluation, we are focusing on them. Also, what we can see is that relational and no-relational variant of the AVOC analysis seems to have a much greater impact than the choice between existential and universal propagation. For the precision analysis, here we report the analysis with the interval domain, and we just report the 2 drivers for which we have a precision loss. What we can see here is that we have a precision loss in about 4% of the invariant. But if you're looking at the constraint that made up the invariance, we were able to compute up to 99% of the original constraint. Of course, here we are not focusing on time, since intervals are already very fast, and it's difficult to see efficiency improvement. But for the polyhedra domain, what we have here is a representation for all the drivers. And what we can see is that, yeah, we do lose precision in about 50% of the time, but we are able to compute circa 90% of the original constraint. And sometimes, usually, we are less precise in an invariant, but just by 1 or 2 constraints. What we can see here is that usually existential and universal propagation behaves in the same way, whereas sometimes universal, it's highlighted there, it's it's preciser. But also, we have some interesting cases for which we are analyzing the speed up later, for which we do not lose precision at all. So, talking about speed ups, here you can see in blue the original times for our test, sorted from the longest to the shortest time and expressed in seconds, while in orange you can see the time for the target analysis with our approach. I want to mention that the time expressed in all orange also includes the data flow analysis and the program transformation step. So as you can see here, you usually have speed ups, and they vary from long programs to short programs with an average of 2.61. Another interesting thing to say is that the time expressed in blue are computed and are similar to the times computed with the ELINA library, which is considered state-of-the-art. So talking about the test that had no precision loss at all, we were able to measure that it has always a speed up of 1.60, which is interesting. And whereas for the biggest speed up that we have, it's for a short test, but we have a speed up of 8.23%. And also, this happens for the longest test, which was avoking up to circa 80% of its statement, and we have a speed up of 8.16, sorry. So concluding, in this work, we obtained significant speed up to 8.23%, with an average of 2.61. And we suffered limited precision loss, because we were able to compute circa 90% of the original constraint. For future work, we are looking for further simplification of the CFG after our AVOC processing, which is composed of the data flow analysis and the program simplification step, and we are looking to improve heuristic, either to improve efficiency furtherly or to have less precision loss. So in this work, we showed how to propagate lack of information. Thanks for your attention.
Thank you, Greta. So we have questions here.
Does it work? Yes.
It does.
Thank you for your talk. So you mentioned that you have both false negatives and false positives. Do you have an intuition how often that actually happens?
Not really.
It's just from the high-level idea.
It's from the high level, yeah. The high level, it's an heuristic. We have no precision requirement, no correctness requirement. So this is implemented as a heuristic. We know this is subject to both false positives and negatives. But at the moment, we didn't do any statistics about how often this happens.
Okay, thank you.
Yeah, Jérôme?
Thank you. I have 2 questions, if I may. Okay. So thank you for your talk. It's very interesting. My first question is, a common source for having unconstrained variables is loops when you are unable to find an inductive invariance. Do you have ideas to extend your work to deal with this fact?
At the moment, no. This is just a lightweight pre-analysis, which is a computation of a fixed point on the CFG. What we can say is that the analysis always terminates, and we're happy with that because we are working, of course, on 2 finite lattices and with a monotonic function. But at the moment, we do not focus on loops.
My second question is about the fact that you transform assignment have you considered other approach, like, for instance, guiding partitioning to be precise for the control flow path when you have when you know that variables are constraints, and to be very imprecise on other control flow paths?
Okay, no, at the moment we didn't consider that, but that's interesting. So yeah, of course the idea is to target the statement that are useful to say something about the variables, so to infer some properties about the variables. So yeah.
Okay. Thank you very much.
So thank you for the talk. I guess, yes, okay. So I guess the analysis as you presented this seems to be intra-procedural.
Yeah.
Did you think about making it inter-procedural or not?
At the moment, no, because the tool in which we implemented the analysis has the inter-procedural mode, but it may suffer some precision losses. But what we did was inlining the function in order to be more precise.
Okay, thanks.
Well, I will also ask one question. So when you talked about false negatives, you did show an example, and I was wondering whether this could be solved with a slightly finer grained notion of likely unbounded, where you would distinguish likely unbounded by below and by above. Did you look into finer grained likely unbounded constraints, or is it just?
No, this is just the implementation. We did not go into finer conception of likely unconstrained, but for
Do you think it would make sense?
yeah, it may have sense. Of course, the more you're able to distinguish between likely unconstrained and not likely unconstrained, the less precision you're losing at the end, I think.
One more, Jérôme?
I think that's quick. Thank you for your presentation. That's a bit specific, but about CRAM-diff, I was wondering how the difference of precision was measured. Is it like a percentage of missed assertions, like missed properties proved?
No, just focusing on invariants computed, and what the CLAM-diff does is for each program point, it compares the invariants computed by the two different analyses semantically, and then it outputs whether they are different, and we then checked how different they were. But since one of the benchmark wasn't annotated for assumption, we just worked on the invariants. Then, of course, the invariants we are computing may be used for a certain assumption.
Okay, so that's a kind of volume of error that was missed, precision that was missed?
Yeah, the precision is computed on the invariants, and then we looked at the number of constraints in the invariants to see how far we are from the original invariants.
Okay, thank you.
Andy?
Have you any thoughts on how this might carry over to octagons, because they're quite interesting, because like small octagons, when the degree of the octagons is relatively small, work great, but once you're working with large numbers of variables, there are real memory performance there, partly because of issues such as caching, such as accessing these big arrays. So if you could detect that a variable was not required, you could then reduce the dimensionality of your octagon, and that might give a big performance win and be something perhaps between the amount of pruning you get with intervals and the less aggressive pruning that you get with polyhedra. Have you any thoughts on that?
That could be the case. Yeah, I think that the more expensive and the more precise the domain is, the more benefit you can get from this kind of approach and pre-analysis.
Okay, cool.
Okay, maybe we have, no, I don't think we have time for last question. I think we had a long discussion, so thanks a lot for the very nice presentation, triggering. Okay, good. So the last talk is about modular optimization-based round-off error analysis of floating point programs. So this is work by Rosa Bruejani and Eva Duralova. And Rosa is going to give the talk. Thank you.
So, hello everyone. I'm going to talk about modular round-off error analysis of procedural floating point programs. Suppose we have a complex number a plus bi, where a and b are real values, and we want to compute the radius of this complex number. So the formula looks like this, and it has many applications in geographical allocation, secret analysis, and so on. Computing the same expression in a computer in reals is not feasible, or if it were, it would have been very expensive. And so the same expression in a computer looks like a function like this one when we are using double precision floating point arithmetic. And the floating point arithmetic uses finite number of bits, and that introduces round-off error. And the round-off errors are the distance between the real value and the floating point presentation. So these errors possibly and most probably make the results incorrect, and at the same time, floating point arithmetic is used in critical systems, and we would want verified tools and rigorous correctness guarantees for such systems. So that is why we need to provide guarantees for the upper bound of round-off errors. So I'm going to first introduce some notation and the running example for our talk, and then continue. So we use the tilde symbol to represent floating point operations and values. And so suppose we have a real valued specification of function f and its floating point implementation, where the input parameters have input intervals and also initial errors. So our goal is to compute the round-off error, which means maximizing the difference between the real value and the floating point counterpart. And the main challenge is how to compute accurate bounds. Computing the exact difference is not feasible, or is only feasible for smaller computations, and so we need to over-approximate the results. On the other hand, this formula as it is too complex to reason about, because it's a combination of two theories. So it's a combination of the floating point and the real theories. And for example, we cannot just rephrase it as a SMT query, and since solvers have little to no support for combination of these two theories. So this is what we are after, and it's too complex. One approach is implemented in the FV Taylor tool. So assuming the rounding mode to nearest from the IEEE standard 754 for the floating point arithmetic, then this rounding model holds for floating point values, variables, constants, and operations, where epsilon bounds the relative error E and delta bounds the absolute error for the normals D. So we apply this rounding model on the floating point abstraction of f, floating point function of f, and we abstract it into the real valued function of f hat. So now our computation is entirely real valued, but it's still too complex for optimization tools to handle. And FP Taylor, to reduce this complexity, applies Taylor expansion on the floating point abstraction of function f. So this is the first order Taylor approximation, and it allows one to approximate a sufficiently an arbitrary sufficiently smooth function with a polynomial term. Taylor series defines infinite expansions. However, if we choose a suitable point R to compute the approximation around, and then we can, these terms, we get a finite number of terms that are error terms in our case, and they include the first order derivatives and a remainder term that bounds the rest of the error terms, and for our case, or bounds the other higher order terms in general. So we apply the Taylor expansion on the floating point abstraction of our function f around point y, z, 0, and 0, and we get this. So there are the first order derivatives, and we also have a remainder term that bounds the error. And please note that since we are setting the e's and the d's to 0, then it means that we don't have errors, and so this f hat equals to f of y and z. So we have a concrete way of computing the an upper bound for the error by maximizing this expression over a given domain. In short, FP Taylor first computes the abstraction of function f, and then it computes the derivative symbolically. It then evaluates the above expression or maximizes the above expression using rigorous optimization techniques such as interval arithmetic and branch and bind. So we can say that FP Taylor computes the error in 2 steps, an abstraction or simplification step and a solving or optimization step. FP Taylor has support for transcendental functions, but they have well-defined derivatives. However, it does not have support for procedure calls modularly, meaning that we need to inline these procedure calls before applying FP Taylor, which means we will have very large expressions and large analysis time, as we have observed in our evaluation. So we have proposed a sound modular round-off error analysis for non-recursive procedure calls without conditionals, procedure code without conditionals. Our approach combines modularity and abstraction when analyzing procedure calls. And we have implemented our approach in a prototype tool called Hugo. And finally, we have an empirical evaluation of the accuracy performance of our analysis. Next, I'm going to explain our modular approach. So, in our modular round-off error analysis, we have extended the FP Taylor approach to also support procedure calls. Let's assume that this is the same example as before, and now it has been rephrased to have function calls. We can see that G is called twice here with different arguments that both have different intervals, and both of them are within the allowed range of G. For the simple case, now we assume that we don't have any input errors, and our analysis computes the error in 2 steps. The first step is the abstraction step, where we compute error specifications for each procedure of the program, and we use its interval for computing the error specification. Error specification is a function of the input intervals of the procedure. So here, beta of G is the error specification of G, and beta of F is the error specification of F. And we reuse beta of G in computing beta of F only symbolically at this point. So, and the step 2 of our analysis is the instantiation step, where we instantiate the error specifications that are pre-computed now with the suitable context and at the call sites. So our goal is here in producing the error specification is that how to produce them such that they are abstract enough to provide an improvement in the performance, and on the other hand, they are not too abstract that we lose too much accuracy. One naive approach is to just compute a concrete error bound for each procedure. However, it loses too much accuracy. At the other hand, just pre-computing the derivatives does not lose accuracy. However, then we would have a modest performance. So we would want something in between. So in step 1 of our analysis, we extend the rounding model from before to also handle procedure calls. So for G, the abstraction is as before because it doesn't have any procedure calls. And for F, we treat the beta of G as a symbolic variable. We treat the procedure call of G as symbolic variable. So we abstract G with a real valued result. And an absolute error as the round-off error. Note that this round-off error, its value depends on the input variable of f, so it depends on y. So, I should point out that we do not need the concrete error specifications at this point for, of G at this point when we are computing the error specification of F. So again, we proceed as before with applying the Taylor expansion for G's as before. And for F, we apply the beta of G's as similar to the E's and the D's and as symbolic variables. So we would have first order derivatives with respect to the betas. Already at this point, we try to improve the performance by abstracting those smaller terms that do not affect the accuracy much. However, they would improve the performance if we evaluated them now, and then we wouldn't need to reevaluate them repeatedly at the instantiation time. And specifically, we are evaluating the first order derivatives with respect to the normal errors and also the remainder terms that do not have any beta terms themselves. So in step 2 of our analysis, which is the instantiation step, we instantiate each error specification of each function recursively using its input domain. So for here for beta of f, when we are instantiating the error specifications of G init, then we use the input intervals of f. So we also check that before instantiating these procedure calls, we check that the input interval of the input parameters of these called procedures encloses the input interval of the arguments of these because we are using them. And so as I mentioned before, we have a trade-off here since we are pre-computing some smaller terms. We improve the performance. However, since we are potentially using wider ranges for evaluation, then we lose a bit of accuracy. As for correctness, so if we inline the beta of G's in the beta of F, then we would get the same round-off error formula that we would get if we had inlined all the procedures in F and then computed the error specification. So now let's assume that we have input errors. I will just give you a high-level idea, and the paper has more details. We use the triangle inequality and split the error into computing the propagation error, which is the error resulting from the initial errors, and a round-off error, which is the error resulting from the arithmetic computations. So we compute the error specifications in two parts. A propagation error specification, which is the gamma function here, and a round-off error specification, which is the beta function. And so for our example, the gamma of G is the propagation error specification of G, and the gamma of F is the propagation error specification of F. So to compute the propagation error specifications, we again apply the Taylor approximation, however, this time with respect to the input parameters. So we implemented our approach in a prototype tool called Hugo. Hugo is on top of Daisy. Daisy is an existing round-off error analysis tool. And we have chosen two case studies to evaluate Hugo over them. We chose this case study because we expect the modular analysis to be more beneficial in these settings. Each case study has several procedure calls, and also some procedures may be treated as library functions that are called in other procedures. And each procedure also contains arithmetic operations and computations, and it potentially has procedure calls and also a precondition that describes the allowed ranges for that procedure. So we have two case studies, one with matrix operations and the other with computations over complex numbers. And also the XL and XS version of those two case studies have a smaller, have fewer or more procedures. Meaning that, we added these case studies so that we could evaluate the scalability of Hugo. So we compared, as part of our evaluation, we compared Hugo with two of the state-of-the-art tools, FBTailor and DAISY. We chose FBTailor because it implements the baseline symbolic approximation, Taylor expansion technique, and it has been shown to outperform the other tools. And we chose DAISY since DAISY implements a different type of analysis. It's a data based on data flow analysis, and it has been shown to be generally less accurate. However, then it is a bit faster. It's often faster. So. And we compare Hugo with these tools. And since neither DAISY nor FBTailor supports procedure calls, we inline the procedures before running DAISY and FBTailor. And similar to Hugo, when we are reporting the runtimes, we report the runtimes of producing errors for all the procedures of one case study. So, and these are our results. Hugo is faster for all the case studies except the complex XS case study, and it's often significantly faster. And this is with computing errors that are often within the order of magnitude of the errors that DAISY and FBTailor generate. And FBTailor is not able to compute a round of errors for two of the largest procedures of the complex case study that have a lot of procedure calls. But Hugo is even able to produce error bounds that are tighter than DAISY. And this is due to DAISY using a different type of analysis that is known to be less accurate. As for the complex XS benchmark, we expect this result that Hugo is slower. And this is due to the fact that our analysis has an implementation overhead that makes it more useful when we have a lot of procedure calls and a lot of code reuse. So to conclude, we have shown how to extend the optimization round of error analysis approach with support with procedure calls, and in our evaluation, we have shown an interesting trade-off between the performance and accuracy, and we have shown that our analysis is able to produce shorter runtimes. Our tool accepts on purely procedural code at the moment. However, we expect our approach to be used in existing modular verification tools. And finally, Hugo is available. It's open source and it's online. You can try it if you want to take a look.
Okay, we will now move to questions. Okay, in here.
Nice talk. Is it working? Okay, nice talk, thank you. And I was wondering, you had as a restriction that you only consider straight line code. Would it be difficult to extend it to at least conditionals, which might be interesting, I guess?
Yes, that's an interesting question. Our goal was to just apply our approach on this current optimization-based approach and see how it works, but we did not aim for a fully a tool that supports all the features of all these features, and we think that this handling conditionals is another open research question, so we didn't.
Okay. Any other question? So I do have one. The use of expansion with Taylor series reminded me a little bit of a rather old tool which was called Fluctuate, done by Mathieu Martel, Eric Goubot, Sylvie Buteau, except that they were not really quite using the Taylor expansion itself. They were more like using a bunch of coefficients which were essentially related to imprecision on each input of a program. And I was wondering whether you looked, at least from the formal point of view, how it compares. I'm not sure the tool is still easy to find around, but the approach seemed a little bit like both related but different, because you are using the Taylor expansion and they are not quite doing so.
We did not compare with Fluctuate, but so I don't know. But
Was,
I don't think they handle procedure calls though.
No.
Yeah.
I mean, I believe it's also fairly old tool. I'm not sure it's still available at this point. Yeah. Any other question? I'm checking online too. So, yeah, there is one here.
Maybe I missed it. Can you repeat what you're actually doing with the arguments to your function? So you mentioned that you might have multiple ranges for the same procedure, and so what do you actually do with them? Do you union them, or so do you analyze just for one?
No. So when a procedure is called, then it's called with the parameters of the calling procedure. And then those input parameters, the input intervals for these parameters should be enclosed by the input ranges of the call procedure, so that we could actually use the abstraction that we pre-evaluated the smaller terms in the first step.
Okay, thanks.
Okay, so if there is no other question, I propose to thank again Rosa and close the session. Okay, so we have a half an hour break now.
Hello. So thank you for coming to the last session of SAS. I'm very honored to share this session. So the invited talk will be given by Loris D'Antoni, and we will see how to analyze infinitely many programs at once. So we are very interested.
Oh, can you hear? Let's see. Yeah, I'm there. Awesome. OK, everybody can hear me. Good. So now we can move beyond the catchy title. And so this talk is as the talk says, about verifying programs. And I assume many of you have seen this. You have a precondition, a program, and a postcondition. That's program verification of one program. Today, we're going to verify many programs. So we're going to have, the idea is that we're going to have some inputs on which we want to run many possible programs, and we want to satisfy a postcondition. So in this case, what we want is that all of those programs satisfy the pre-post condition. Cool? The setting is good? And the important question is, why do you want to do this? And the whole story is Happing's PhD dissertation, which was a very successful PhD. He is now a scientist at AWS. So it was a good PhD because he found a job, which is the main goal in life, I guess. Well, one of the main goals, besides all the other fun stuff. And basically, the story of his PhD started as follows. And I'm going to tell you why it's a successful PhD story, because it kind of came. It's a good lesson today if you're a PhD student in the room, that sometimes what you're going to work on comes later on in your PhD. You actually don't know it to start when you start. So Happing was working on this problem. This was his first problem I gave him. Like, look, people write these programs for modifying strings. They're called encoders and decoders. And it feels kind of silly that whenever we write an encoder, like the program that takes a string in one format and turns it into another, we also have to write the decoder. Because once you encode the string, there is only one way to decode it. So can we synthesize the second program automatically? And Happing's insight was that instead of synthesizing these really big programs, you can focus on little bits of them. And you don't need to understand what this program does. But the idea was that we can reduce this big synthesis problem to small synthesis problem. And we were very happy, because at the time, there was this thing that came out, which was called syntax-guided synthesis, which was promising to be able to solve small synthesis problems. So if we knew to solve small synthesis problems, we could also solve big synthesis problems. And what is syntax-guided synthesis? Is a framework where you write a specification in some form of first-order logic, and you say, I want a program S that does a bunch of things. This program, you don't need to read it, is the specification of the max of two numbers. And you give a search space, which is a grammar of programs, and you say, I want you to find a program in this search space that satisfies the specification. And then the synthesizer will go and look for one such program. In this case, for example, if x greater than y, return x else y, it's a valid implementation of max. Therefore, it's a valid solution. Here is another solution. It's just a weird syntactic rewrite of the same program. OK? So there are tools out there called Cygos solvers that if you give the thing on the left, on a good day, they give you the thing on the right. OK? And people have used Cygos for a lot of things. I'm not going to talk about those in this talk, but if you're curious, there is a lot of applications. OK, great. Happing was very excited. So he was basically taking things like this, these little lines, and encode them. I'm not going to tell you how, but he's going to encode them as synthesis problems. And then he was going to call a solver. And in this case, this is one possible solver. And he was getting good solutions like this one. You don't need to understand what that is, but it looks nice and small. And we like nice and small when we have to write programs. But sometimes he called a different solver, and he got a different solution. And this was CVC4, what he was given at the time. So that doesn't look like a small program. In fact, it's bigger than the program we start with. And you don't need to read it, because probably you can't also physically. But basically, this program says, if the input is the bit 1, the output is the bit 7. If the input is the bit 2, the output. So and this is for an 8-bit bit vector. So correct, not great. OK. So program synthesis was unpredictable. Basically, you were in this situation where if we changed from the grammar representation we had before to a visual representation, you have a search space of programs, the grammar, and you have a set of valid solutions. And in this case, what we had is that there were two valid solutions that they were both correct, but one was better than the other. And the point is that at the time, there was no way to say which one you prefer. A solver could give you either of these, and they were valid solutions. There was no way to say, I prefer one over the other. And so here, I want to focus on Happing's face. So at the time, he was very happy. But then when this happened, he became very sad. And look what you can do these days with artificial intelligence. Yesterday, in just 20 minutes, I could make happy look sad. And nobody had solved this problem. And so Happing was a little bit frustrated at the time because he was like, he wrote this paper and this tool kind of was throwing crazy solutions. And this is the kind of the point, that the lesson for PhD students that are sort of in your first year. This will happen. You will get stuck. But when you get stuck, you can either be sad, which is a valid answer, but also you can see this as an opportunity. Basically, we found something that the state of the art was failing at. And this was a great opportunity to actually work on something hard that people hadn't thought about. And this what I just showed you basically led to the whole line of work that I'm going to present in this talk. Okay? So basically, Cygos was not able to say, I prefer one program over the other. And Happing came up with this thing called QCygos, which is a very simple idea. I'm not going to show you how it is defined, but the idea is that it allows you to give preference over syntactic features of the program. So for example, there you could say, I want the program with the fewest if-then else's. Okay, so the first program had 0 if-then else's. The one synthesized by CBC4 had millions. So you want the one with the fewest. And so when you do that, then Happing had a very clever technique that basically could use existing Cygos solvers to solve this problem. And the technique basically will do the following. It will find a program. In this case, let's say this one. And then it will modify the search space to only accept programs that were better. Okay? It will come up with a new grammar that only accepts smaller programs or programs with the fewest if-then else's. And now you can do this, and you can do this, and eventually you get the best program. Okay? That's the optimal solution. And here came the big problem. How do I show you that that solution is the best one? What I have to do is I have to produce a proof that all the programs in the red space are wrong. Okay? If I want to show to you that this solution is the best one, I need to show you that any program that is left is incorrect. And we wanted the proof of that, and instead what we were getting was timeouts. Fail, non-terminate. So the solvers were just like going to start running forever and not find a solution because they were very good at finding solutions, but not at proving that one wasn't there. And now I think you get the connection. So basically, this is called unrealizability. So I have a specification. I have a grammar of programs. In this case, there is no program of this form that can compute the max of 2 numbers. And what we wanted was the answer unrealizable, which is a proof that there doesn't exist a program that satisfies the specification and lies in this search space. And this sounds like a verification problem. So that's why we want to verify infinitely many programs at once. So basically, just to rewrite it, what we want to have, and this is kind of where things get interesting, I want that for every program in the search space, I want to prove that there exists an input that falsifies the specification. Okay? S, though, here is a program, okay? Is not a first-order term. And the challenge here is that there may be infinitely many programs. And for each of them, the witness might be different. So to prove that each program is wrong, I might need to check it on a different inputs. Let's look at this with an example. So this is the example I gave you before. The specification here, again, you don't need to read it, but it says this computes the max of 2 numbers, x and y. And this is the search space. You can do x plus 1, x plus 2, x plus y plus 10, whatever. There is infinitely many programs. That's the important part. And I want to show that all of them are wrong. So let's look at possible inputs. So here I have 3 inputs. Input 0, 1, the max is 1. Input 1, 0, the max is 1. Input 0, 0, the max is 0. And there is 3 possible programs, x, y, 1. So what's interesting here is that if I take any of these programs, each of them satisfies 2 of the examples and fails the other. So again, the input falsifying the example is different for each of them. And in this case, things are actually pretty good, because you can only come up with finitely many inputs for which you can get programs that differ. But I will show you, if we have time at the end, there are cases where you need infinitely many possible witnesses for infinitely many possible programs. Okay? So 2 challenges. Potentially, we need to reason about infinitely many programs. Potentially, we need to reason about infinitely many falsifying inputs. And this brings us to kind of the first slide we saw. So you have an infinite set of programs, or a large set of programs, some set of programs, and you want to prove and assert something that says on every possible program input, each of those programs produces a wrong output. Okay? So now we are in familiar territory. And as I said, you want to prove this for every S. OK. Now that I showed you why we care about solving this verification problem, and I'm going to show you more examples at the end, I'm going to show you what we did in this work. So having led the first 2 efforts on this, and as I said, this is kind of story of a successful PhD, it started with something that had nothing to do with this, but again, like research kind of comes to you in weird angles. It led to this work that kind of, it did this very nice work that I'm going to show you first. And then I'm going to show you the work from my current student, Jim-Woo Kim, that he then took this to really a whole new level beyond new applications. And so in particular, I'm going to first show you some techniques that are specific to Cygos. So we just saw this synthesis framework that we care about. And then I'm going to show you the first work that then moved these ideas to reasoning about arbitrary programs, like imperative programs. And then finally, I'm going to show you work from this year where we have actually a logic, like Hoare logic, to reason about these infinitely many programs at once. OK, let's start with the first paper. So like all first papers on a topic, it's going to be very easy. And, but it's good. It's that we were proposing a new problem. We didn't know what we were doing. And so we came up with the easy solution, which is what you want to do. So you have a Cygos problem, so a synthesis problem with a specification and a grammar. And I'm going to restrict now that my specification only comes through examples. So I have, in this case, 4 examples. They kind of show is the max function. So the max of 0, 0 is 0, and so on. And what I want to show, what I'm going to do, I'm going to show you that we can build a normal verification problem, like a classic reachability problem, such that the assertion in the program always holds if and only if this problem is unrealizable, meaning this synthesis problem has no solution. The nice thing of doing this is that at the time, it wasn't obvious how to do it, but once we did it, we could use existing solvers to do so. OK, let's look at the idea. And the whole paper is in one slide. So, well, 1 plus a few more of why it doesn't work. So, OK, so what I'm going to do, I have my inputs. In this case, there is one input. I want to show that on the input 1, 0, I want to check whether there exists a program that can output 1. So in this case, I'm going to start with one example. And I'm going to put that example in 2 variables, x and y, x0 and y0. So now here comes the magic. And this is where things get interesting for people who work on verification. I'm going to have a magic function called fstart that non-deterministically picks a program in my search space and runs it on x0 and y0. So this basically takes any program in the search space, 1, non-deterministically, and runs it. And I'm going to show you in a second how to do that. And computes the output on x0, y0. And now all I need to do, if I can do that, I need to assert that that output is wrong. Is not, I wanted 1 is not 1. So if this assertion problem, if this assertion is always true, it means that no program in the search space satisfies this example. So I'm going to do it for one example now, OK? So how do I build a program that non-deterministically runs all the possible programs in my search space? Well, basically, I'm going to mimic the grammar that is given to me. So I have this grammar of the programs that I'm trying to run. I'm going to non-deterministically pick a production each time and run the corresponding program. So if I'm running the program 0, all I have to do is return 0. If I'm running the program x, I need to return the x component of my example. Things get a little bit more interesting when you do recursion for productions that build bigger programs. So I'm going to non-deterministically build 2 subprograms, run them, and combine the output. OK? So this is overly simplified, but this is really the idea in the paper. And I hope this is really nice, though, because it shows exactly what we showed at the beginning. I basically have a precondition, some set of examples I'm running. I have some sets of programs I'm building, and then I'm verifying an assertion. And the assertion here holds if and only if this is unrealizable. So in this case, this particular problem will be realizable because there is only one example. In particular, there is a program that on input 1, 0 returns 1, the program 1. So we need to put more examples. So this works. It can handle the case that we have infinitely many programs, but it cannot guarantee that we are falsifying, that different programs falsify different examples, because I've only given you one example. So here comes the tricky part, and I want you to pay close attention to the point in this slide because it's subtle, and is one of the key points that distinguishes the problem I'm talking about from many other verification questions. the program I built guarantees that on that example, so the assertion will fail, meaning I can get a program that actually outputs 1, if there exists a program that outputs 1 on this example. If I create a new problem with a different example, the assertion will fail if there exists a program that outputs 3 on those examples. But these two problems together don't mean that there exists a program that is correct on both examples, if both assertion fails. So what I need, basically, there might be different programs. So in this case, there is this issue that I need to synchronize my inputs. I haven't checked that there is a program that is correct on both examples. I've only checked that there is a program correct on one and the program correct on the other. So I cannot compose assertions in the usual way. So what we needed to do in this paper, and again, this is a crucial point that is going to kind of, we'll have to piggyback for the rest of the talk, to make sure that the program is not correct for the synthesis problem. It has to be wrong on one example, but we still need to feed all the examples at the same time. So in this case, we will basically execute simultaneously each program we sample non-deterministically. We need to execute it on all the examples. If we have 2 examples, you need to compute the 2 outputs kind of in parallel. And at the end, you check that one of the outputs is wrong. So in this case, this new problem I wrote will say this assertion fails if some program is correct on both examples. And dually, this program verification problem will be good, the assertion is true, if all the programs are wrong on at least one of the 2 examples. Okay? So this is one of the key new things. So from now on, basically, in all the rest of the techniques I'll show you, I'll bring with me all the examples together. I will never try to solve for one example at a time. You cannot do that. OK, so it seems like we solved the problem. And when we did this, basically, we built a tool that does exactly what I just described. It takes a synthesis problem in Cygos. It reduces it to a verification problem, a reachability problem, and use it at the time we were using Seahorn, and we could verify. And here are some cute things we could prove that came from the paper on minimizing Cygos problems. We could prove that to do the max of 2 numbers, you really do need an if then else. If you do it without if then else, you cannot do it. The max of 3 numbers, you cannot do it with 1 if then else. To do the XOR, you can not only use and or if you don't have negation. There might be other restrictions here I'm not mentioning, but this is kind of at the high level. If you want to sum 2 numbers and you don't have access to the variable y, you cannot try to do x plus 1, x plus 6, x plus 7. So simple examples that basically came from solving synthesis problems where our goal was to optimize some objective. And this, at the time, was the first of its kind. So we were the first that could do any of this. Existing solvers, when you will ask, can you solve a synthesis problem that has no solution, they will just crash. OK. Now I gave you kind of the obvious technique, which is like, let's reduce to something that we already know how to do, but can we do better? Can we come up with specialized technique for these different problems? So usually, when you start a new problem, this is, again, like advice for new PhD students, don't try to be fancy from the very beginning. Do first something that kind of works, and then you can improve it. But don't start by improving your work. First, do something. And we did the something, and now we understood some problems that were arising, and we were able to address them directly. So I'm going to show you the next technique is, thanks to my colleague Tom Reps that at the time pointed us to it, is this thing called grammar flow analysis, which is kind of a forgotten gem in the verification community. And so I'm going to resurrect it today for you. So what is the essence of what we are trying to do? OK, so I'm going to move away from reachability and Seahorn and whatnot. I have a grammar. So this grammar basically can produce programs of the form 1, 2x plus 1, 4x plus 1, and so on. OK? And really what we are trying to do, if we have 2 examples, in this case, 1 maps to 5, 2 maps to 6, we are trying to reason about the set of possible outputs that every program in this grammar can produce on those inputs. So in this case, if I feed the inputs 1 and 2 simultaneously, I can get the output 1, 1 if I run the program 1, 3, 5 if I run the program 2x plus 1, and so on. Right? That's what I just showed you in the previous slide was kind of doing that. And what I want to do is just check whether my output, in this case 5, 6, the 2 outputs are 5 and 6, is this one of the possible outputs that I can produce? So if I can check that, it means the problem, if 5, 6 is a possible output, the problem is a solution. If 5, 6 is not in that set, the problem does not have a solution. It's unrealizable. Okay? But now we are in a problem that seems like, okay, maybe if I can just come up with the representation of that set, then I can just check this directly. I don't need to encode a crazy verification question. And that was essentially the key idea here. The key idea here is that we can use all the beautiful abstractions that we know from abstract interpretation, and we can come up with new ones to model what this set is. So in this case, very simple one, this set happened to be one that only contains pairs of odd numbers. Okay? I removed the grammar, but you can convince yourself that that's the case. Once you convince yourself that that's the case, if I can prove that indeed that's a valid abstraction, all I need to check is that 5, 6 is not in the set, because 5, 6 is not a pair of odd numbers. OK, now all I have to do is show you that to convince you that that's indeed the solution. And here comes the beautiful grammar flow analysis. So grammar flow analysis is just data flow analysis applied directly to context-free grammars. And we have a grammar for us, so it seems like a good fit. And this is all it is. I'm going to go slow here and pay careful attention. So I'm going to take my grammar. I just spread it out for what I'm going to do next. This is my grammar from before. And I'm going to just do abstract interpretation on the grammar. So I'm trying to compute the set of outputs that E can produce, that I defined that to be E sharp of 1, 2. And then what are the outputs that X can produce? Well, X is in this case is the input examples. So it's the pair 1, 2. And I'm going to abstract that. Plus, everything is going to be abstracted. And notice that there is a recursive call to E sharp 1, 2. So the definition of this is an equation. This is basically an abstract equation. And now I can solve this by applying my abstraction. So in this case, E sharp 1, 2, I said it's odd, odd. 1, 2, it's odd, even, clearly, because 1 is odd and 2 is even. And everything else is going to be like that. And now if I solve this equation, I get odd, odd equals odd, odd, which means that odd, odd is a valid solution to this equation. And grammar flow analysis just gives you conditions under which this is sound. Basically, it just says, as long as you can find a solution to this equation, your solution is a valid abstraction for that set. And it's actually a little bit better than that, but the clear point here is that I just proved to you that odd, odd is a valid solution there. In particular is what I'm going to call an invariant. It's to get to familiar territory. And once I prove that, I basically solve unrealizability. Now, all we needed to do was to come up with these invariants automatically. OK? And that part I'm not going to show you, but what we showed in this paper, which thanks to kind of rephrasing the whole problem as this grammar flow analysis, we were able to find family of problems for which these invariants can always be computed, and they can actually be exact. And what that means, I'm going to show you in this case, we showed that for SIGOs, where the specification is only given as examples. And the grammar is a subset of linear integer arithmetic, so the examples we had before was 1. For that case, we can always compute exact invariants using grammar flow analysis. And what that meant is that by just moving away from this arbitrary verification problem, we had found a fragment of the problem that was decidable. And this was the first result of its kind. There were actually many papers showing that everything was undecidable about synthesis, and here we have found one case in which it's decidable. And you can read the paper if you're curious about this. That's the PLDI-20. But so this was exciting, because now for the first time, we had realized that this problem was not an arbitrary verification problem. It was something we could exploit the structure of. And not only that, besides the nice theory, when we built the tool based on grammar flow analysis, we built a tool that was faster than the previous one on every possible input they could solve, and it could solve new benchmarks. OK? So things were looking good. In fact, Happing was very happy at this point. In fact, he graduated and he found a job. But so the point, it all started with a problem that had nothing to do with this, which was inverting encoders. So again, story of a successful PhD. I think this is very nice. Like, we started with something, and we identified a key problem that people hadn't looked at. And then, really, it led to a lot of research. OK. I'm doing well. Good. Time is good. Now I'm going to move to something that is a little bit more esoteric. So brace yourself. OK. So far, all I showed you was how to solve problems where we have they felt like simple problems. I think that's probably a lot of you in the audience, like, oh, I think you're telling us you're verifying infinite many programs at once, but your programs are like X, 1, and 2. And that's not exciting. We want real programs. So to move to actual programs, we needed to handle imperative constructs. Okay, so we want to handle loops, we want to handle all the stuff that people like to reason about in verification. So I'm going to show you now why that is. If what we did before was already pretty hard, what we're going to do now is really, really, really hard. Okay, so the game changes completely. And it took us, so actually this paper I'm presenting, it took us 1.5 years with Jinwoo to come up with sort of the solution I showed you. And we were solving a different problem at first. I mean, before we were solving a different problem. But we spent so much time trying to understand what we were solving that the insight I'm going to show you in the next couple of slides, it took us 2 years to come up with. So now it's going to be obvious, like all things in retrospect. But it was very tricky to move away from the view we had of Cygos. OK, so the example I showed you before had this form. So what is so special about how we solve this problem? When I wrote the equations that then I turn into grammar flow analysis equations, I use a very important property of Cygos, and that in Cygos, all the programs you generate are expressions. They are not imperative programs. They are not stateful. They are just expressions. So they are x greater than 0, x plus 1. So things that have a type Boolean or int, but they are not state transformers. Okay? What that means is that when I write these equations, I know, because of the semantics of expressions, that the value of x is fixed. Okay? Variables don't change in expressions, don't change their values. And so I could write these equations as follows. I know that x is always going to be the pair 1, 2. My input is not going to be modified throughout the execution. And clearly, this is not true for imperative programs. So here is a new synthesis problem. So now we have our grammar contains imperative. We're basically trying to find a program of the form nothing or x equals x plus x followed by x equals x plus x followed by x equals x plus x as many times as you want. So clearly, and our goal in this case, I want to show that on the input 1, I want to produce the output 5. This is unrealizable because if we look at the possible values that this can produce, there is only 1, 2, 4, 8, and so on and so forth, right? This program computes powers of 2 in some form, and 5 is not a power of 2. So how do I prove that all those programs, all the programs in the search space are wrong on this input? So how do I prove that this problem is unrealizable? Well, let's try to do what we just did. So I can try to do grammar flow analysis, but now I need to change. So notice before I start that before I had this E of my inputs was the set of outputs, but now I have set S of my input valuation is my set of output valuation. So S says that if I start with x equals 1, I can end with x equals 1, or x equals 2, or x equals 4, okay? So now if I try to define that set, I guess, so the values that I can end up with when I start with x equals 1 is, and now here I have this recursive equation. And the problem is that at that point, x has changed to 2. So to reason about what values x equals 1 can produce, I need to reason about what values x equals 2 can produce, right? Because after I do this first assignment, that x equals x plus x, x has changed to 2. So that equation is correct. That's the correct definition. But now there is a new variable, x equals 2. So I need to solve for x equals 2. And now there is a new variable, x equals 4. And in particular, this never ends. To solve this grammar flow analysis problem the way I showed you, I will need an infinite set of equations. And we don't like that, because it was already hard enough to solve for finitely many variables. We don't want to try to encode something that has infinitely many variables. So we need to do something else. And again, I'm kind of spoon-feeding the solution here, but at the time, it took us a long time to actually understand what we were doing. And the abstract interpreters in the room will be like, well, you need something relational. Of course, you need to capture the input and output values, not just the inputs. And surprise, surprise, that's what we do. We introduce relations. And so basically, the point is that instead of this S of an input, really what you want to have, you want to have a different relation, let's call it SEM-S, which captures the semantics of any program in S. So in this case, SEM-S of CD holds, the relation holds for C and D, if starting on input x equals C, there is some program that can produce x equals D. And now, if I can compute that relation gives me everything I need. That relation captures the semantic of all programs in my set. Okay? So how do I compute that? So I can try to do it with kind of grammar flow analysis, but really at the time then we realized that that was not going to work very well because it was very hard to come up with relational domains that they were precise enough. Instead, when we were working on these, what was becoming particularly hot, and now it's, I think, very hot, was using constraint-or clauses. And so this is another connection to something that you're all very familiar with. I could actually define what it means for a relation, what it means for a pair to be in that relation. I mean, constraint-or clauses were, I guess, around for a longer time, but here it became very clean to connect them together. Basically, all I'm saying in this implication that you see here is that if I want to model the update S goes to x equals x plus x s, I can do this inductively by saying, well, if C2 can go to C3 in S, so I'm basically modeling this side here, and C2 is equal to C1 plus C1, then C1 can go to C3. So I'm just defining the semantics of that operation inductively. So this is really the semantic of sequence in sequential composition in statements. OK? So all good. This seems pretty obvious. But now is going to come the problem that was really the actual problem, and that's the one where we got stuck for a long time. And I think that's going to be a bit different from what you're used to. So this example is going to be tricky to follow. So again, a good point to re-wake up if I put you all to sleep. So I'm going to show you a very simple problem, which we have a solution, is OK, we don't know how to do well, and the goal of this keynote today is that you tell me how to solve it. So be all careful, because I know you have the tools that I don't, so I want to make sure you understand the problem. I have this very simple grammar. A contains two statements, x equals x plus 2 and x equals x plus 3. And now I have a loop. The loop repeats one of the two programs in A twice. The semantics here is one of them. It's either x equals x plus 2 twice or x equals x plus 3 twice. So one might think that this relation can be defined as whatever the semantic. So let's go back for a second. The semantics of A, the relation, is every pair of numbers that some program in there can compute. So 0, 2 can be computed by x equals x plus 2, 0, 3 with x equals x plus 3, 1, 3, and so forth. When I take their product, like I do there, which is what you will do in a compositional technique if you only had one body of the loop, I'm in trouble. Because in the product, I also consider the case in which I interleave what loop body I have at each iteration. So in particular, this allows to do x equals x plus 2, followed by x equals x plus 3. So this for unrealizability is sound, but massively imprecise. I'm basically looking for an invariant that only uses program variables, but that is true for an infinite number of programs over those variables. And that's going to be very, very hard to find. OK, so this is a key point. We call it the shifting sense problem. So tell your friends about the shifting sense problem. But seriously, we don't know how to solve this well. We have a solution, and we have a theoretical solution as well. But this is the key essence of the challenge of proving unrealizability, is that you need to remember what program was run, not just what behavior it produced. And the solution in this particular paper was that then, instead of having the relation just talking about inputs and outputs, we needed the relations to remember what program you were actually running. So in this case, we are not building just a relation that says this input can lead to this output, but really we are basically effectively building a full program semantics of the form the input gamma, when fed to the program TS, produces gamma 1. And now, how do we define this relation? Well, the good news is that there is a whole community called PL community that writes things like this. And basically, it's literally just operational semantics. In fact, we got so excited about this that we built a whole format for describing this. And that's a different talk if you want to look at. But it's called SemGus, which is basically SciGus++. But long story short, you have now a way to describe. Essentially, what I'm describing with this relation is, in this case, the bottom says gamma on while TB do TS produces gamma 2 if gamma TB produces the value V, and so on. And now you can write constraint-or clauses to describe all of these relations. So that's just a constraint-or clause. But if you look on a PL textbook, it just looks like different notation. OK. So once we saw this, we were basically back connected to something that the SAS community knew how to solve, which was verification problems. And in particular, we started with something that looks like this. So I have a grammar of imperative programs. So in this case, a grammar of a bunch of things that can loop. And I have their semantics given as constrainer clauses. And these I can write it manually, or it can be extracted automatically from most programming languages. And then I have some examples. In this case, I want that on input 6.9, the output of the first x is 15. And this is just an example that shows I want to compute the XOR of those two numbers, the bitwise XOR. And if you remember before, I kind of told you the XOR cannot be computed using just AND and OR. And in fact, none of the programs in here on this input can set x to 15. Okay? This is going to be important in a second. And now, to solve this problem, to solve this unrealizability question, because I have everything set up as CHCs, all I had to do was one step. I had to write one last CHC, one last constrainer clause. I'm not going to show you how, but you can also encode the syntactic structure of a grammar using constrainer clauses. So you can inductively define what programs are in the grammar by just following the rules of the grammar. So this says, can you give me a program T in this grammar such that if I run T on input 6.9, I get 15 something. And the semantics relation star, remember, is defined by those semantic relations we defined before. So the cool thing is that the top part, you only need to do it once for each language you want to do unrealizability for or verification for. And then at the end, you're just going to ask queries of the following form. So we are back to a normal verification question. It's like, can you give me a program T that is correct on the inputs? Well, if you can do that, you have proven that T is a solution. So if you can prove in constrainer clauses that this result is reachable, solution T, you have found the solution to the synthesis problem. Dually, if your solver can show me that this query is false, it cannot be proven, you have proven unrealizability. And it turns out that existing solvers, in particular Spacer, are much better at proving that there is no program than proving that there is a program. And that's what we did. We built a tool that essentially will take a grammar of imperative programs and examples, and it will spit out a CHC query over a bunch of CHCs, and then it will use the tool Spacer to check whether the query was possible, had the solution. And here, we had a bunch of simple small examples, but I want to show you just some cute ones, that these are things that, again, like, you know they are true, but if you think about how to build a proof, it's a bit tricky. So we could prove that you cannot swap two variables if you don't have an auxiliary variable and you don't have XOR or a plus. So you cannot swap two variables x and y if you don't have some either additional storage or expressive power in the language. And you cannot do the XOR, the example I showed you of two-bit vectors, if you only have AND OR. Even if you have infinitely many possible loop body or whatever, it doesn't matter, because you're never going to be able to build what you need. And we built a benchmark suite, and we could solve about half of it. And but yeah, essentially, we were able to, for the first time, to prove that something about infinitely many imperative programs. So these are complex programs. OK. So if you were asleep again, this is another exciting part to wake up, because now we go into the grand finale of this thing. OK, perfect. So remember, this thing is basically, I cannot do the XOR of two variables unless with only AND and OR. And when we fed this to a CHC solver, the way it proved, actually, that this was not possible, that part wasn't the important part. What it was interesting is that it came up with this invariant. And this is an invariant that I promise you had never seen in your, well, maybe you've seen, I don't know. But most likely you haven't seen an invariant like this before. So this is an invariant that says, you don't need to read fully, but basically it says all the programs in this set the third bit of x to 1. So you've seen a lot of invariants of the form, the third bit is always 1. But this is different. This one says every program in this set is an invariant that is true for infinitely many programs. An invariant specifically tells you this invariant is true for infinitely many programs. Okay? It's different than a loop invariant, which is something that just says true. This one says, no matter what program you write, this is true. And once we saw this, again, story of a successful PhD, this led to the next paper. We were like, wait a second. That's what we were missing. We were looking for invariants about inputs and outputs, But what we really need to do is to look for invariants about sets of programs. So the invariant cannot only talk about the relation that the problem specifies, the invariant needs to talk about what program is building that relation. And that's what I need help from this community, and that's going to be what I'm going to end with. But like, how do we build such invariants? We don't have abstract domains for talking about sets of programs. Or with the ones we have, they're not quite there yet. And so really, this was the problem. Unrealizability, and in general, these verification problems, to solve them fully, you need to build invariants about infinite sets of programs. And this Jim would then write this paper, which I think I love it personally, is basically he came up with a logic, like Hoare logic, for talking about sets of programs. And so this is what normal Hoare logic looks like. So you want to show that if I start in P and I run S, I end up in some subset of Q. Our new logic lifts this to sets of programs, and we call it unrealizability logic. That was a faux pas. We should have called it infinitely many Hoare logic or something, I don't know. Because it doesn't have anything special to unrealizability. It actually can be used for reasoning about any problem of this form. But basically it says, if I start in P and I run S1, I get here. If I start in P and I run with S2, I get here. If I start in P and I run in S3. So if I pick all those programs and I get some sets, the triple is true if any of those programs ends up in a subset of Q. Okay? So it looks like we can reduce everything by doing, it looks like we can solve the thing on the left with the thing on the right with the thing on the left, but we cannot, because if you understood everything I said in this talk, just reasoning about inputs and outputs is not going to be enough. We really need to remember which program produces what. So that's kind of the key part here. I'm going to be very brief on this part of the talk. But if you really want to be able to have a complete logic for reasoning about this problem, you cannot just do things of the form P as Q. You really need to talk about, your logic needs to capture what happens within the set S. Okay? And so if you read the paper, there is a lot more on this. But that's really the challenge. But I'm going to show you, and why does this tie to unrealizability? So in normal program verification, you use Hoare logic to say PS not bad means that nothing bad can happen. If you want to prove unrealizability with the logic on the right, what you're going to show is that all these programs cannot satisfy the specification. Okay? Okay. So I'm going to still draw some analogy with normal Hoare logic so that we kind of are in a good place here. But if you want to prove something like, one nice property of Hoare logic is compositionality. If you can prove things about individual programs, when you put them together, you prove things about composed programs. Okay? So that's captured by rules like the rule for sequencing that says, if you can prove that S1 goes from P to Q and S2 goes from Q to R, then S1, S2 goes from P to R. Okay? And we have a similar rule in our logic, but notice that this is now a little weird. If you can prove something about a set of programs and something about another set of programs, their composition is the Cartesian product of all those programs. So I can take any of the programs in the two sets and run them in any order. Okay? And that's what our rule captures. So notice like I run x1, x1, x1 by 2, and so on. So we get this nice property again that because of the definition of the problem, we get compositionality. So I'm going to show you an example. I'm not going to show you the rules of the logic because it's pretty complicated, but I'm going to show you some of the insights. And in particular, the key insight is this invariance about infinitely many programs. So how do I prove? I'm going to show the example with the non-imperative statement, something like just expressions. But we know that invariant from before, that if I start with x equal 1 and y equal 3, I always get an odd number. How do I prove this? That this grammar always produces an odd number with x equal 1 and y equal 3. So the idea, this is the triple I want to prove. I want to prove that if x is equal to 1 and y is equal to 3, the output, I'm going to call it VE, the output that I produce is odd. To prove this, I'm going to have to prove that this is an invariant of my search space. This is an invariant of all the programs in the search space. And the way you do it is basically, I'm going to have to prove it by assuming that this is true. So this is similar to relational summaries in procedural verification. So to prove that something is true for a recursive program, I have to assume it at each recursive call and then prove it for the main program. And here is the same idea. To prove that that is true, I have to prove that assuming that hypothesis, I can prove that it's true for every possible production in the grammar. So in this case, assuming that this is true, can I prove that it's true for x? Assuming that this is true, can I prove that it's true for y? Assuming that this is true, can I prove that it's true for e and e? So the case for x is, I'm going to use I and O as shorthands for the premise and postcondition. So let's start with this one. This one is very easy. So for x, how do I prove that starting with x equal 1, I get an odd number? Well, x is already 1, so the output is 1. And with a weakening, I can show that the output is always odd. And similarly, I can do it for y. So this is just, right now it looks like normal Hor logic. Now the interesting stuff happens here with the recursion. How do I prove this? So now I'm using my inductive hypothesis. In particular here, the premise is the same as what I'm trying to prove. So E satisfies this invariant because I'm assuming that E satisfies this invariant for both of the sides of E. And now, basically by induction, I'm doing a proof by induction. Now, how do I prove that E and E satisfy the invariant? Well, that's just the semantics of n. If I take two odd numbers and I take their end, their bitwise end, I get an odd number. So really the key point here, if you want to remember anything, is that the logic contains these invariants where the center E is not one program, is a set of programs. Okay? E is the set of all programs derivable from E. And the logic allows you to do proofs by induction over the syntactic structure of the grammar. And if you can do this, in this case, you basically establish that this is indeed an invariant. And with everything you saw in the talk, this means that the problem is unrealizable. I cannot show you everything, unfortunately, so there is too much to cover. But the logic is much more complicated because it has to capture all the issues that I highlight in this talk. In particular, remember we said you need to run all the inputs at once for unrealizability, otherwise nothing works. So the input is not going to be an input anymore in the sense of a variable. It's going to be a vector of inputs that I'm going to thread to my program. And some proofs, if you want completeness, require the vector to be infinite. For loops is a mess. We don't have a good compositional rule for loop. We have a rule that is sound and complete. So the rule in the paper, actually, we just found a bug in it. So coming soon in the next week, there is going to be an errata published. But we fixed it. It's a small fix. But it's very tricky to do it for loops because of what I showed you before, where the loop body can change. But assuming with this fix, we have the first logic that is sound and relatively complete in the sense of our logic. And we also, the cool thing is that this logic actually subsumes everything I showed you in the talk. Like every technique we showed you, we can now translate it as finding invariants in this logic. Like the logic is a complete proof system for everything I talked about so far. I'm going to show you this cute example. This is an example where to build a proof that all the programs are wrong, you need infinitely many inputs. And it's super simple. I'm trying to come up with a program that computes the identity function. But all my programs are of the form if x equal a constant returns a constant, with as many if then else's if you want. So this example is cute because no matter how many inputs you give me, I can just put enough if then else's to make it correct. I can choose if x is equal to 1, return 1, if x is equal to 2, return 2. But no matter how many you give me, I can find the witness. But to prove that this is actually unrealizable, you need something like this esoteric invariant over infinite vectors. So if you have a good solver over infinite arrays, so we're using Vampire now, but if you have a better one, or you think you can reason about invariance of that form, please come and talk to me because we need such a good solver. Okay, just to end real quick, I talk all the time about unrealizability, but I want to get you excited because I assume that none of you cares about unrealizability. I probably am the only person in the world that cares about, but actually it's a very important problem, and I'll show you why it's an important problem. So here is another problem where such a logic or such a system could be helpful. So this is a paper from FSC 18. So what they were solving here is that they have a program, and some piece of the program is missing. Actually, they're trying to come up with that piece of the program. Oopsie. OK. They're trying to come up with that piece of the program. So there is a I'll tell you the story. We improvise. No, everything is same signal. Oh, that's a good question. That could be the problem. Oh, I ran out of battery. Oh, that was my fault. OK, we'll finish improvisation. OK, so the point I'm trying to show here is that I'm trying to find a program that is correct. I'm trying to find the missing piece of the program. And I cannot do that. So to do that, that paper uses symbolic execution over a program that is missing a piece. And when you do that, basically, they get too many symbolic execution paths. So all the paths, you get exponentially many paths like in normal symbolic execution, and they want to prune away the ones that are infeasible. And pruning those paths away is a form of what we are just doing. You want to show that no matter what program you put in the hole, the paths are not possible. The next application I was going to show you is, and that's the dream that started this whole project, is can we do CDCL for program synthesis? So if you want to do CDCL for SAT solving, what you build is proofs that some subset of the space you've explored is not leading anywhere. And we don't know how to do that for synthesis. So in synthesis, you're searching for a space of programs. And now, at some point, you get like, oh, I'm in a place where I'm stuck. This is leading nowhere. So we know sometimes how to realize that we are stuck, but we don't know how to learn why we got stuck. And the invariants I showed you earlier, they give us a hope that we can build these proofs that maybe are reusable of why I got stuck. Okay? So in the same way in which CDCL can create blocking clauses, can we create blocking synthesis clauses through these invariants? And the last application is if I get my code from an untrusted source. So in JavaScript, you can have this eval statement that basically takes a string of code and just runs it. And I know this community has written papers about how to reason about that type of code, but in general, it's very hard because the code comes as a string, and I need to reason about what it does. So I can either non-deterministically assume it does something, but I can try to reason about it explicitly to a logic like this. In particular, if I know the grammar that code can come in, maybe I have some restricted language that code can come in, this logic allows you to talk about that. Okay? So unfortunately, that's my fault. I forgot to plug in the computer, so I paid the price. But that was the end of the talk. The last thing, basically, I wanted to leave you with, I have a logic that allows me to reason about unrealizability. And this logic allows me to talk about infinite set of programs. And the things I was going to ask for your help with is how do we build invariants for sets of programs? And for those, we will need good support for infinite vectors, for abstract data types, because we can use data types to model programs. And that's it. Thank you.
So thank you very much. It was fascinating. So questions?
Hello.
Yes.
So this is very interesting, and I think it's oddly connected with type systems in the sense that you are saying for all the programs that follow a certain grammar, then certain properties, certain invariant hold.
Mm-hmm.
A type system said for all programs that are well typed in this specific type system, that it can be an extra layer of type system over others, then certain properties hold. So have you thought about the relation between this extended hold logic and the whole area of type systems?
Yeah, so that's a great question. The question is basically like, oh, this sounds a lot like type systems. So there is first the easy answer, which is type systems and verification a la Hoare logic. They are all very connected indeed to start with. Like in general, well, one is targets different type of programs. The other one, but in general, you can translate the inductive principle of how you do verification together. Now, how to map it to these sets of programs? So it's true that one type system that you specifically design allows you. It's a bit different though, because you design it for a set of programs, but they produce proofs for one program, typically. Like when you give me a type in derivation, it's decoration of one program.
Yes and no.
Okay.
The grammar is the type, instead of being restricted to...
Okay.
In a type system, instead of being restricted to a simple BNF grammar for the program that will have to respect this property, you have a much more complicated criterion that is the existence of the type proof. Mm-hmm. But then, in the same way, you say for all programs that verify this grammar, properties hold, a type system says for all the programs that verify this type system, those properties hold. So we just have a richer constraint where instead of just being a grammar, it's a more complicated but still usually inductively defined logical restriction.
So I think it is in principle possible to come up with something that decorates the grammar itself. And in a way, that's what we did. Yeah, the question is, can you reframe it as a type system? And I think the answer in general, there is a lot of connections in general with how we do verification in the abstract world or in the abstract interpretation world or logic and type system. So I think the same connection should be established here. Yeah, and I'm looking forward to somebody doing that. Yeah, thank you.
Yeah, thanks for the nice talk, Loris.
Yeah.
This is more of a check of my understanding of intuitions, but it seems like the shifting sands problem is very similar or related to kind of like the program alignment problem where you're doing differential analysis or relational Hoare logic or something.
Yeah.
Can you
So
elaborate?
that's a great point. So if you only have finitely many programs, then in fact in our logic you can do something easier, which is basically you can take the case analysis of those. The alignment in the tradition, like the issue is that program alignment works really well when programs align. So most of the techniques are kind of assume that because the program is itself the same most of the time, then the alignment is somewhat easy. In our case, the programs are completely different. And so, but you can have a program that is a loop in the search space and a program that has something completely different. And so we don't know how to do the alignment in a way that is meaningful. That's kind of the issue.
Right, so like exactly, like when you're doing differential analysis, you typically assume it's the same program or structurally very similar, and that's where you can get proofs. But exactly when they're semantically the same but syntactically different, that becomes hard. So is that
exactly? Yeah. So we don't know. That's exactly where right now we don't know how to build proofs efficiently when the alignment doesn't happen.
Got it.
So we need to rely on a constraint solver to tell us, oh, we can do something.
Okay, Katrina?
Okay, thanks. So when you talk about invariance of sets of programs, another connection that comes to mind is, well, what some people call hyperproperties. Have you?
Yeah, so actually it's, that's a great point. And the reason it took us years to also do a lot of these things, because we asked the same questions you're asking, and every time we thought that was the solution, and then we realized that we were looking at the program wrong. And I think these are all things that essentially everything you're saying, it can be put on top of this reasoning. So the hyperproperties part is like, how do I prove unrealizability in the sense like, how do I prove that all the programs in my search space are non-commutative? Now you need hyper reasoning on top of this. But hyper reasoning doesn't give you this by itself, because you still need to remember which program was running. But you're very much right.
Yeah, but when you reason about sets of programs, the invariants are talking about properties of these sets of programs. So in a sense, when you have some analysis that can do hyperproperty reasoning, maybe you can use it to find invariants about some of these kind of problems.
I think potentially, I think you might be right. Potentially, to some extent, you can find it. If there is finitely many, I have to think about the specific analysis you have in mind. But yeah.
I don't have any analysis in mind. I'm saying, and hypothetically,
Yeah.
hyperproperty analysis that could find invariants maybe can help with solving some of these problems.
That's true. Generally, I think these two words are very connected, the sensitivity analysis and the hyperproperty. And I think a lot of it comes down to subsets for which you can find alignments. And if you have one program, these things are always possible-ish. Like the issue for us is like, even if you take the simplest grammar, they all look very different. I'm back connected if you want. Yeah, perfect. So.
Okay, so I have one question related to the first and the last one, and then I will give a parole to Andy. So do you have abstract domains that come to your mind to abstract a set of programs?
Yeah, so that's essentially the part that I'm struggling with. And first, thanks for everyone who paid this work. But that was my last slide. Essentially, this thing on data types, that's the question. So right now we are relying on Spacer, for example, for the third work I presented. And Spacer somehow can build internal invariants about data types. And they have various weird representations. But there is really no good work on saying, here is a set of programs for which something holds. So we need something about good abstraction for data types. I know people have looked at this in the world of shape analysis back then. There was one way. I mean, data structures were effectively kind of similar reason. We really need to reason about trees in some form. But I think this really requires a fundamental rethinking of, we need some relational domain that effectively decorates trees with their meaning. So something that is like trees of semantic triples of their domains. And so this requires to design new domains. And I don't know what to do in this case for the sets of programs. Like we have some very simple things like, oh, you can get prefix abstractions. Every program that starts with this prefix, this proof is going to hold. And that's what you're going to get for the CDCL example I gave, where basically any program that I can complete from this partial program is going to fail because of this reason. In particular, on the input 5, is going to output a number greater than 6. So that's an invariant. And now if I can build a lot of those in a very nice form, maybe I can do something smart. Yeah.
Thank you. Andy?
There's also a question here.
After, oh, okay.
Yes.
Yeah, so I found the idea of grammar flow analysis to be particularly intriguing, and specifically when thinking about SIGUS in general, because you have these choices of, do I fill out this part of the candidate program that I'm synthesizing, or the other part. And so I was wondering if you had looked into using this abstraction to automatically prune search space while you're doing SIGUS.
Yeah, so that's actually, there was another application that I had when my computer died. But that's a great point. It's like, if we can compute the abstractions, if the issue, there is this issue with profitability with synthesis, that pruning is only good if it prunes more programs, that if the time it takes you to prune is less than how much time it will take you to explore a good chunk of the program in the space. So if the invariants are too expensive to prune, that's not a good idea. But we have techniques that some of the solvers that we are building do that. They prune based on these ideas. There was actually a follow-up paper from our second paper, the grammar flow analysis paper, that they built a simple pruning strategy based on abstractions. They didn't frame it as grammar flow analysis, but effectively they had a very cheap abstract domain that whenever possible it will prune, and it was very effective in practice because it was very, very cheap. So it's like, very rarely something was unrealizable in the subpath, but when it was, you could throw it away in a way. So it's a great idea, yeah.
So I guess as a follow-up question, how much of this program logic are you able to automate through like abstract interpretation, and how much of it is manual?
Future work.
Fair enough.
I have a student now that is basically working on that. How do we automate it? And he has built automation, so we can do simple proofs. But invariant checking is extremely hard, infinite vectors and whatnot. Invariant generation, we have no idea. So we can use SIGUS to generate trivial invariants, but anything complicated that involves quantifiers like the one I showed at the end with the for all, then we don't know. But yeah, I would love, if anybody has ideas, yeah, I would love to hear those.
Okay. Andy?
I think the intuition behind the first question is correct. I'm sorry my brain works slowly these days, but there was a best paper in Lobster about 2 or 3 years ago, and it was a PhD student who used the Curry-Howard isomorphism to constrain the space of synthesizable programs, and he used that to improve the synthesis process. So that might be worth looking there.
I think I'm familiar with the word. So in general, in the synthesis word, there are many words, but one of them is sort of type-directed word, and you're very much right. Typically, they don't look at grammars, I believe. Like the one, maybe the particular paper you have in mind is something different, but usually they look at, so usually you have a type in judgment, and you're trying to do type in habitation and trying to find the term, a program that has the proper type, and the type is the specification. And now you can explore using type-directed synthesis. You can use the rules of your type system to explore the possible derivations. And then at some point, you will get you get a local proof that there is no inhabitant for the local problem you've solved. So I'm saying it's very similar in principle. The challenge here is the grammar restriction. And sorry if I didn't make that clear enough. Like, there are many synthesis formulations out there, many of which are always solvable in particular, because if you ask me, is there a program that does something and you don't restrict the search space, then the answer is yes, unless the problem is undecidable. And typically in type-directed synthesis, they look at search spaces where there is a nice type system you can design. Once you restrict the search space, and that's what we, maybe I should clarify, what we tackle today is not the synthesis as in second-order quantification in logic, where you say, is there any term that does the thing? I'm asking, is there a term in this very constrained syntactic search space that does the thing? So that's really what breaks inductivity and makes it very, very hard to do reasoning. Yeah.
I'm sorry, we are already late, but you can ask offline.
I'm around, yeah.
So thank you very much for your talk and your answers. And we are going to go to the next talk. Yes, please applaud. So the next talk is given by Ben Mikek. and it's about mutual refinement of context-free language reachability.
Hello, everybody. I'm Ben Mikek, and I'll be presenting mutual refinements of context-free language reachability. This is work by Shuo Ding. I'm presenting it for him because, unfortunately, he couldn't be here today. So I'll do my best to be a maximal under-approximation of what Shuo would have said today. And this is work at Georgia Tech with both of our advisor, Chirun Zhang. So I'm going to structure this talk by giving first some background on the formal language reachability problem. Then we'll talk about the existing approaches. Then I'll introduce mutual refinement, which is our novel approach to solving the problem. And then we'll discuss some experiments that show the power of mutual refinement. And finally, we'll close with some discussion of future work. So context-free language reachability is a widely used program analysis framework that can be used to encode many different program analysis, static analysis problems. So we start with a program and some property we're interested in verifying, and it could be really anything you're interested in. And one strategy for answering this problem is to translate the program into a graph and the program property into a graph property. So depending on the particular analysis we're most interested in, this could be one of many different types of graphs. It could be a control flow graph, a value flow graph, lots of different possibilities. And the strategy is going to be then, if we have some property of the program that we're interested in, some static analysis query, we want to translate that into a query on the graph, and in particular, into a question in the form of reachability. So we're interested in whether one node can be reached from another in the graph. However, it's not just a question of reachability in the graph. We impose an additional constraint on it, which is that the path, we only are interested in certain paths in the graph. And in particular, we're going to label each edge in the graph with an element of some formal grammar. And then we're only interested in reachability along paths for which the labels of edges in that path form a string that is generated by the grammar that we specify. And through this, this is formal language reachability, and we can use this to express many different program analysis properties. So as an example, if we just have this two-line program where we assign AF from source, and then we assign sync from A.G. We can generate a very simple program for this that looks like this, where we have nodes for each of the values. And then the edges are labeled with these brackets that are labeled with F and G. And in this case, we have the semantics of the program are represented in this graph on the right. And finally, we have to specify a language. So in this case, this is called a Dyke language, where we have matching pairs of parentheses. But in general, we could have any kind of CFL we want to as labeling these edges. So in this case, in a Dyke language, we're interested in paths being reachable if the labels along the paths have paired parentheses, or in this case, we represent them with brackets. And in this particular example, that is not true because we have an open bracket with F and a closed bracket with G label, so the sync is not reachable from the source in this example because the path isn't generated by this Dyke grammar. Now, there's a well-known algorithm to solve the context-free language reachability problem in cubic time. There's been work on this going all the way back to 2000. But there are some program analysis problems that require more complex former grammars that are not CFLs. And that's where we get into why mutual refinement may be useful. So let's take as an example a taint analysis where we want to have both context sensitivity and field sensitivity. So in this case, we're going to represent this by interleaving two different CFLs, one for each of those two parts. So for context sensitivity, we have the CP language, which I'm going to refer to as the parenthesis language. And for field, that's a Dyke language. It's just paired parentheses. And for field sensitivity, we have the CB, which I'll call the bracket language. And that consists of either paired brackets or unpaired open brackets, but we can't have closed brackets that aren't paired with something. So both of these are CFLs. The second one isn't a Dyke language. And in interleaving them, what we're interested in is paths along the graph which form strings that can be generated by each of these grammars separately. So we're interested in the interleaving of these two grammars. and the interleaving of these two CFLs is not a CFL. And in fact, in work in 2022, it's been shown that the reachability problem for formal languages that are not CFLs is undecidable. And even, in fact, just interleaved Dyke languages, reachability in that context is also undecidable. And so every solution to this problem will be inherently an approximation. And what we're interested in is, can we improve upon the approximations? So I'll start by talking about what's the current approach to doing this, and then we'll talk about how mutual refinement can improve on that approach. So we have this example graph, which is in the two languages I described before, the parenthesis language and the bracket language. And we're going to use the two CFLs to over-approximate the reachability here by essentially performing reachability analysis one at a time. So in the first case, first we'll run the parenthesis language. And so we're going to trace all of the edges that contribute to reachability between any pair of vertices under the parenthesis language. So if we do that, for example, in this purple line, I've marked the path from S to T. And the purple line shows that T is reachable from S in the parenthesis language because we just have the paired open and close parentheses 22. In addition, for example, A is reachable from S because actually for the parenthesis language, that's just an empty string because we aren't interested in the interleaving yet. If we do this analysis separately for the bracket language, CB, T is also reachable from S along this red path that you can see. I'll note we have a paired brackets for second between S and A and P2 and RET2. And then we also have an open-only bracket, which remember is possible in the bracket language here. So T is reachable from S, and there's also some other pairs that are reachable, like RET2 from S. And so the traditional approach to solving this problem would be to take the intersection. So we run reachability in each language separately, and then we take the intersection of the reachable pairs that we found before. So in this case, in particular, T should be reachable from S because it's reachable in both languages. But there's a problem here. This is a false positive. Why is it a false positive? Well, the path from S to T that's valid in the parenthesis language, the one marked in purple, well, it's not valid in the bracket language because it has an unpaired closed first bracket. And the path that's valid in the bracket language, it's not valid in the parenthesis language because we have an unpaired open parenthesis 25. And that means that this running CFL reachability on each language separately and then intersecting them can produce false positives, so it's not very precise. And our idea is to iteratively modify the graph by removing edges in order to solve this problem. That's mutual refinement. So the general approach is we start with the original graph, we run a modified version of reachability, in this case for the bracket language, but for whatever our first CFL is, to produce a smaller graph. So we remove any edges that don't contribute to reachability between any pair of vertices. Then we do the same thing for the next language, in this case for the parenthesis language, to produce an even smaller graph, G prime prime. And we do this iteratively. That's the key thing. So we run each language one at a time, we remove edges one at a time, and we run this process iteratively until we reach a fixed point. And that's how mutual refinement differs from the original approach. We're doing this edge collection at each step instead of just taking an intersection at the end. So I'll talk a little bit more formally about how mutual refinement works. In traditional CFL reachability, we have kind of the first part here, which is tracing edges. So the approach is to trace the edges that contribute to reachability between pairs of vertices, and then we can come up with a set of pairs of vertices that are reachable from each other. What's different in mutual refinement is the edge collection process. So we still do tracing for each language in each round, but then we collect the edges and mark them. And I think the easiest way to think about that is if we were removing them from the graph. But that's more kind of a way to think about it more than an actual implementation. So the process is we trace for each CFL, one for each CFL in each round. We collect the edges that are relevant to that, and we do this iteratively until we reach a fixed point where the edge set doesn't change anymore. So this is very abstract, and I think the best way to think about this further is with a more concrete example. So we'll return to this same program that originates from a taint analysis problem. And we're going to show how mutual refinement can solve the false positive that we saw before. The languages are the same, the parentheses language and the bracket language. So in the first round, we're going to trace, arbitrarily, we're going to decide to start with the bracket language here. And so what edges don't contribute to reachability between any pair of vertices in the bracket language? Well, the closed bracket between P1 and ret1 is like that, because it doesn't have a pair. It's not contributing to reachability between P1 and ret1 or any other pair of vertices. And so we can remove that edge. We collect it and remove it from the graph. Next, we do the same thing with the parenthesis language. So we're going to trace all of the edges that don't contribute to reachability between any pair in the parenthesis language. And this is where we really start to see the benefit of mutual refinement. Because now, open parenthesis 22 and closed parenthesis 22 along the top, neither of those contribute to reachability between any pairs any longer because we removed the edge in the middle. So both of those can now be removed. And in addition, this open parenthesis 25 along the bottom path can also be removed. Now we run a second round, again starting with the bracket language. And now, because we removed that edge from A to P2, the closed second bracket in the bottom path also doesn't contribute to any reachability, so it can also be removed. And now I think we can see that neither of these two parentheses that are left contribute to any reachability because we've removed the path that connects them, so they can also be removed. And now let's suppose we wanted to do a third round of this. Well, if we wanted to remove another, if we were tracing brackets again, we only have open brackets left. And remember, in the bracket language, open brackets are fine, so they contribute to reachability between S and A or between X and T, for example. If we did tracing for parentheses, well, there are no parentheses left, so certainly we can't remove any more edges, which means that if we ran another round of this, we wouldn't change the graph, and we've reached a fixed point. And from this graph, we can quite quickly conclude that T is not reachable from S. And through mutual refinement, we've removed the false positive that was identified through the traditional approach of tracing and then intersecting. In the paper, we've proven two theorems about this mutual refinement process. The first is that it always reached a fixed point, and in fact, that fixed point is unique. So no matter which order we apply the individual CFL approximations in, you will always reach the same fixed point where you can no longer collect any other edges from the graph. And second, mutual refinement is guaranteed to be at least as precise as the traditional intersecting approach. So no matter what, if you find a false positive with mutual refinement, that will also be a false positive in the traditional intersecting approach. And there should be some false positives that you removed by switching to mutual refinement. These are two important facts about mutual refinement. We also considered the complexity. So traditional CFL reachability has cubic time complexity and quadratic space complexity. And mutual refinement has no worse time complexity. It's also cubic. Both the tracing and edge collection are each cubic, so the overall process is cubic. It does have cubic space complexity, which is asymptotically more than the traditional approach. But for time, at least, it doesn't take, it asymptotically takes the same amount of time as the traditional approach. And V here is the number of vertices in the graph. And so with that, I'll talk, so we've seen that mutual refinement is more precise, is at least as precise as the traditional approach. In addition, we've seen that it has no worse asymptotic running time, but we think that in practice, it should have higher precision and probably not much worse running time. And so we've set out to show that with experiments. And in the paper, we show experiments with two different client analyses. The first is a taint analysis for Android apps written in Java. And this is over-approximated using 2 CFLs. The second is a value flow analysis that comes from Spec 2017 CPU benchmarks that have been compiled into LVMIR. And this is over-approximated with 3 different CFLs. The baseline is the traditional approach I showed you at the beginning, which is to trace reachability with each language separately and then intersect the results. And the comparison is mutual refinement, so the process we just saw. The benchmarks are quite large, so there are several that have more than 100,000 vertices and edges. And yeah, there are 2 benchmarks, one for taint analysis and the other for value flow analysis. And indeed, mutual refinement does improve the precision. So for taint analysis, we saw precision improvements of, on average, 50% over the entire benchmark set. And for the value flow analysis, precision improvements of about 10% over the entire benchmark set. And this comes with some overhead, as we saw, so asymptotically mutual refinement isn't any worse than the traditional approach, but in practice it takes about 2.5 times as long for these benchmarks, and it uses about 3 times as much space. And in this case, we're measuring precision by the total number of reachable node pairs. So if we reduce the number of false positives by some extent, then that's what's being shown in the precision improvement column here. There are a couple of interesting points to make here. So first, I mentioned that we've proven that a unique fixed point exists for mutual refinement and will always converge to that unique fixed point, regardless of the order in which the CFLs are applied. However, choosing a different order of application for the CFLs in each round may affect how quickly we converge to the fixed point. So that's something for future work to consider how to come up with a heuristic to pick which order to apply the CFLs in to speed up convergence towards the fixed point. In addition, in practice, if we know a little bit more about the problem and we aren't interested in just computing reachability for all pairs, then we may not need to run all the way to the fixed point. If we're just interested in a single pair, for example, then we can ignore all of the other edges and only focus on paths that connect the two nodes we're interested in. And if we know other information about the particular problem we're interested in, we may be otherwise able to stop mutual refinement before it reaches the fixed point, thereby improving performance. And finally, there's a previous work on fast graph simplification for interleaved Dike reachability. And it's important to distinguish what we do here from that work because mutual refinement can apply to interleavings of any CFLs. And in fact, it can apply to any formal language because at each step in mutual refinement, we run trace using each different CFL, but those CFLs need not be the exact definition of the formal language we're interested in. They could be over-approximations. And so we can, as long as we can represent the formal language as interleaving of over-approximating CFLs, which you can do for any formal language, then mutual refinement can apply. Okay. So in conclusion, we propose mutual refinement. This is a novel strategy for performing reachability in graphs under formal language reachability in graphs. And it allows us to improve the precision compared to previous approaches. And we prove the existence of a fixed point for mutual reachability. So we show theoretically that it will always reach a fixed point, and the order of application of CFLs doesn't matter for that fixed point. And then finally, through our experiments, we show that, in fact, there is a very great practical improvement in precision. And there's some overhead, but asymptotically, mutual refinement doesn't perform any worse than the traditional intersecting approach. And so with that, thank you for your time, and I'd be happy to take any questions.
So do we have questions in the audience? Yes?
Thank you for the talk. Just a curiosity connected to the conclusion. Have you thought about maybe not starting from context-free languages, but from like more expressive languages, not context-sensitive, maybe, I don't know, index languages, and applying the your algorithm to this kind of language? I don't know.
Yeah, that might be interesting future work. I think, so as long as you can, any formal language, you should be able to over-approximate by interleaving CFLs. So in that sense, you can already apply mutual refinement to it. Whether you could do the same type of strategy with a subset of some particular class of formal languages, it might be possible. I guess you'd have to, so the tracing right now we take from kind of existing work on CFL reachability. So if there were a good process for tracing for your particular class of languages, then certainly you could apply mutual refinement to it.
Other questions? Okay. Do we have questions on Discord? Yes, Ivan?
Great. Thanks for the talk. So maybe it's building on the last one a little bit, but like, can you, I mean, so like, can you think about maybe some generalizations that will allow you to apply the mutual refinement in some more general context with, you know, richer domains or something like this, or just speculate?
Yeah. So I think, I guess there are two parts to that. The first is, so I think mutual refinement could be used to represent anything right now. It just probably wouldn't be very precise, right? So I think it's mostly a question of can we improve the precision by doing better in each round. And so I think in the general strategy, yes, definitely could be generalized. And really, whatever strategy you have for tracing edges should be possible to apply within mutual refinement, really almost without any limits on what it does. So as long as you have a method of tracing which edges contribute to reachability based on whatever criteria you're interested in, mutual refinement will probably perform better than just running whatever process you have on the whole graph and intersecting the results.
Okay, so thank you very much. I think it's time to thank Manuel and José, and I will let them the mic.
Thank you. Thank you very much. I mean, we're glad that it came you know, to a successful end. I don't know if you noticed, but the Springer finally produced the proceedings this morning, so we even got the proceedings, so not that we needed them much. So anyway, you know, thanks to all for coming. You know, one thing is, yes, there will be printed versions of the proceedings. I'm sure not everybody wants them, but if you do want them, the Springer, since they didn't manage to ship them in time, they have volunteered to send them to each one of you by mail for free. So if you want the proceedings, the printed one, to get one at home, mailed, then send us the information that we will ask for. So that you don't have to do anything, just wait for our message. We got the list of all attendants from the organizers 2 minutes ago. And then we will send, you know, we'll send a message reminding you and saying what information we want, which basically is the address. And then if you send us that message on a first come, first served basis, the people that attended the conference will get, you know, the nice book and so on. So thanks very much.
Just say thanks.
Yeah, thanks for coming. See you next year.